David, we are back to complete our deep dive into Newton. So I had so much fun and learning experience with the first part of the Newton series that I'm planning on doing a deep dive into Descartes, Leibniz, and Kant. And this is really essential for my research. It's pretty tedious. Um, maybe my viewership numbers are down a little bit. Um, it's hard to really even place why this is important, besides for the history of science, the history of philosophy. I mean, certainly it's extremely important for the history of science and the history of philosophy. But besides for that, it's kind of like, well, why should this be interesting to you? And looking through, you know, one thing for people who have a mystical bent interest in things like, Kabbalah, dualism, spiritualism, to a large extent, spiritualism of the classical sort dies out with the rise of Isaac Newton. You have, Spinoza, you have the Kabbalist. Most of the major important Kabbalist works are written before Newton and conceptually are much more in line with Descartes. And one of the things we saw interesting, and we'll do more deep dive into Descartes, is the ancient conception that there is no such thing as empty space. And everything has to be independently mediated through something physical, like the vortex theory, and we'll get more deep into that. But Newton paves the way for modern physicalism, even though Newton was a very spiritual person. He was a biblicist. He argued against atheism in a similar way to Descartes, that they paved the way for modern physicalism. And as we saw with the contemporaries Hobbes and Cavendish, that materialism and physicalism was already on the rise in that period, as were claims of atheism. So Newton, you will see there's much more on Descartes and Leibniz, who covered much more contemporary philosophy, because Newton does not have a comprehensive philosophy in all sorts of issues, like ethics and moral philosophy and political philosophy, but the rise of empiricism, which we'll see today, which is more canonized through David Hume, and the completion of the scientific method and empirical sciences of experimentalization. And so a lot of these main controversies from Descartes and Newton, and mainly the British empiricist and the continental idealists. And because I'd focus on Kant so much, I focus on the German idealist. But originally, the idealists more come out of France. And next episode, I've already started preparing. We're going to look at the French counterparts, Descartes and his contemporaries of Mersenne, who had the intellectual circle that eventually became the Royal Academy of Paris, Pierre Gassendi, Antoine Arnault, and Pierre Bayle. And there's more names, like Blaise Pascal was around too, and eventually we'll look at Blaise Pascal. But these streams are already approaching like 7 hours each, just to cover 5 people. So I got to cap them off at like 4 or 5 people. Just time constraint, and that's going to do like 2 days, and it may be worth it for my research. Even though my numbers are way down, because I see it's not necessarily that particularly interesting. Maybe eventually I will try to make more popular streams where I'll just do like PowerPoints and talk about ideas. And right now I'm just doing the due diligence, and it's a huge due diligence because there's such a huge canon of mostly Western, but I mean global. I covered some Eastern philosophy and hope to cover more, but there's such a huge canon of knowledge that's largely unknown and forgotten, so that people largely just say things that have already been said, haven't done the due diligence. It's unclear are they actually adding something useful to human knowledge? So I would like to do that, and just curious to understand, curious to appreciate and understand these phenomenon as a student of science, a student of humanity, human life. Um, just in terms of that, it is interesting to me to research. So I'm actually enjoying this research quite a bit. It's my honor to share it with anybody else that finds this interesting. So yesterday we looked in depth, we overview of Newton's philosophy, and starting from his early writings on optics and gravity through the multiple editions of the Principia to his disputes and correspondence with other major thinkers of the time that really changed the landscape permanently of philosophy. And also how calculus and physics was perfected between the British empiricists and the continental idealists. See with like Descartes and the Cartesians and the Leibnizians that are more interested in like, does it add up intellectually, idealistically, on like a logical consistency, like so to say action at a distance. So Newton, you say, well, what's the mechanism of action at a distance? And we say, well, we don't know, maybe like voluntarism. So God created the world that way. We just know from experimental observation, empiricism, that this is how reality works without an explanation for why or how. So I mean, there's a certain how in an exact mathematical formula that explains physical phenomenon, but a deeper how to how do these mechanisms actually work, especially for gravity, action, and distance, and even talking about force, the difficulty of explaining the change in force. I guess tennis is a pretty old game, but when the racket hits the ball, that the force is exchanged between the racket and the ball. How exactly does that mechanism work? So you could look at like a conservation of energy. Um, there's more modern theories that like be molecular quantum, but it's still largely ununderstood. So we just know, well, something happens. It could be accurately, relatively described by formulas, even though from a metaphysical level we don't actually know how the phenomenon works, just um, how to quantify it and the outcome of its action, as where the continental idealists were more interested in an explanation. So rather than the importance of a mathematical predictive equation like gravity, the continental idealists were more concerned with the problem of action at distance. How does the mechanism work? And therefore, you had the idea of vortex theory, or that there is no such thing as empty space, um, and the philosophical difficulty. So saying Newton saying it just works easiest for quantification to assume this absolute empty space, absolute motion, and then relative to what we could measure. But absolute time, absolute motion, absolute space, and the continental idealists largely rejected these notions because there were logical fallacies on a metaphysical basis, even if they had superior calculative um, potentialities. So these are extremely interesting factors, and the deep dive into the one article mentioned a little bit in the part two, which will eventually start with Ernst Mach and his influence on Einstein and Minkowski for space time, which could be seen as a revival of Leibnizian Cartesian views on space, but unlikely. But still, the question of what is space, these metaphysical questions largely remain unsolved. So even like Einstein's theory of general relativity, special relativity are more in their accepted form computative for predictive ability than explanatory for how reality actually works. And that's why like quantum mechanics is somewhat returned to Cartesian metaphysics esotericism. And when we get more into Descartes and Leibniz, we'll see some of the spiritual possibility and the connection for, I saw Sean Carroll was on Theories of Everything. And, so Newton was probably, what is known, what can be determined by science and what can't be determined by science. Kind of like, the Galilean, Galileo's error, um, like according to Philip Goff, of trying to separate consciousness. So Newton, as opposed to Leibniz, has the subjective, the objective mind independent reality of absolute space, absolute time, and absolute motion that has nothing to do with consciousness. And as opposed to more modern theories of panpsychism, we see that Margaret Lucas Cavendish, who was a contemporary of Newton, was a panpsychist. Although her views, how much Newton dealt with or struggled with. So probably have 3-4 hours of reading today. A lot of this stuff is pretty long. So today we're going to look at in-depth overview of Newton's, magnus opus, his Principia, and this is in 10 parts. And then we're going to look at Hume's Newtonianism and Anti-Newtonianism, and as we saw that Newton's, oh yeah, God bless, really always a pleasure. Newton's calculus and physics that we learn today is largely what was canonized by Euler and D'Alembert, although Newton is credited with the creation of the calculus and the concept of the three laws of motion described by force. As we learn in calculus-based physics with the force through energy, through the double derivative, or motion, velocity, acceleration, and the method of differential equations that is used for that. That was designed by Euler a full 50 years after Newton, who largely completely credits Newton, but perfected a lot of the errors that were made by Newton, and combining somewhat of the Leibnizian system. I think somewhat we say like Newton used like the f of x notation, and Leibniz used the dx dy notation, but somewhat combining those two notations today, that when we learn calculus-based physics, that was created by Leonard Euler, and he perfected many of the discrepancies and errors in Newton, but he basically fully gives credit to Newton for the creation of it. But if you actually looked at the Principia, it wouldn't necessarily make sense with our modern conception, and there are a lot of today would just call errors, misconceptions that Newton presumably created this new science at the time with the best of his knowledge, but took a while to be perfected. And then like planetary motion, you have Lagrange and Hamiltonians and the various methods that we use today. These are all perfections and adaptations on Newton, such that you don't really use Newton from the Principia. Maybe in the olden days, in classical education, which doesn't really exist any day, like the great books. I think it was Sarah Lawrence. There might be a few universities, a few places, a few educators that still use the classics of the West, and even this stuff was written in Latin. That someone would learn Latin and then try to study these subjects by reading the original. And I think it was maybe up to was the name slipping me, like mathematical and science works were written in Latin. I'm not sure if Kant, I don't think Kant wrote the critique. Kant probably wrote his critique in Latin. I'm not sure, maybe at a German edition. I'm not sure if he wrote in Latin. Gauss may have been the last people, or didn't even write in Latin. And then, already when you had Riemann, I think wasn't using Latin anymore. But, the classics, these great scientific works were still written in Latin. And I'm not sure how much use it would be to learn Latin and try to study these original texts in their Latin. And, in the sense, like if Euler canonized the stuff that I don't think Euler wrote in Latin either, but I'm not sure. So, it's important. Like, I'm going to continue doing this, and these are more questions that need to be answered. And through doing this, we'll get a more perfection. So, let's jump right in with a deep dive. Newton's Principia. Newton's Philosophiae, Naturalis, Principia, Mathematica. No work of science has ever drawn more attention from philosophers than Newton's Principia. The reason for this, however, and consequently the focus of the attention, have changed significantly from one century to the next. During the 20th century, philosophers have viewed the Principia in the context of Einstein's new theory of gravity and his theory of general relativity. The main issues have concerned the relationship between Newton's and Einstein's theory of gravity, and what the need to replace the former with the latter says about the nature, scope, and limits of scientific knowledge. During most of the 18th century, by contrast, Newton's theory of gravity remained under dispute, especially because of the absence of a mechanism, in particular, a contact mechanism producing gravitational forces. The philosophical literature correspondingly endeavored to clarify and to resolve, one way or the other, the dispute over whether the Principia should or should not be viewed as methodologically well-founded. By the 1790s, Newton's theory of gravity had become established among those engaged in the research in orbital mechanics and philosophical geodesy, leading to the Principia becoming the exemplar of science as its most successful. Philosophic interest in Principia during the 19th century therefore came to focus on how Newton had achieved this success, in part to characterize the knowledge that had been achieved, and in part to pursue comparable knowledge in other areas of research. Unfortunately, a very large fraction of the philosophic literature in all three continents has suffered from a quite simplistic picture of the Principia itself. The main goal of this entry is to replace the simplistic picture with one that does more justice to the richness of both the content and the methodology of the Principia. And this one has 10 parts and will be quite long. Another topic, thing to note as well, we're going over this, is the parallel history of logic, mathematics, and the formation of science. So mathematics and logic already existed. And then, as we saw in the other one, you had natural philosophy that eventually Whewell, who we already went over in before in the early foundations of science with Poincare, created the term scientist in the early mid 1800s. And we already looked at the major thinkers of logic: Frege, Wittgenstein, Russell, and Brentano, and Newton. Leibniz, on one hand, focuses a lot on logic and even has his own logic. Newton does not necessarily have much thought or connection to logical thinking. So we look at the parallels, like now today, like Gödel's incompleteness theorem, and even philosophy being reduced to logic, but just seeing the parallel between philosophy, theology, mathematics, logic, and science. Okay, and this part has 10 sections. The first half overviews till we actually get to the Principia, and then conclusion about the reception and importance of the Principia. Overview: the importance of the work. Viewed retrospectively, no work is more seminal in the development of modern physics and astronomy than Newton's Principia. Its conclusion that the forces of retaining the planets in their orbit is one in kind with terrestrial gravity ended forever. The view, dating back to at least Aristotle, that the celestial realm calls for one science and the sublunar realm another. Just as the preface to its first edition has proposed, the ultimate success of Newton's theory of gravity made the identification of the fundamental forces of nature and their characterization in laws the primary pursuit of physics. The success of the theory led as well to a new conception of exact science, under which every systematic discrepancy between observation and theory, no matter how small, is taken as telling us something important about the world. And once it became clear that the theory of gravity provided a far more effective means than observation for precisely characterizing complex orbital motions, just as Newton had proposed in the Principia, in the case of the orbit of the moon, physical theory gained primacy over observation for purposes of answering specific questions about the world. The retrospective view of the Principia has been viewed in the aftermath of Einstein's special and general theories of relativity from what it was throughout the 19th century. Newtonian theory is now seen to hold only to high approximation in limited circumstances in much the way that Galileo and Huygens' result for motion under uniform gravity came to be seen as only holding to high approximation in the aftermath of Newtonian's inverse square gravity. In the middle of the 19th century, however, when there was no reason to think that any confuting discrepancy between Newtonian theory and observation was ever going to emerge, the Principia was viewed as an exemplar of perfection in empirical science in much the way that Euclid's Elements had been viewed as the exemplar of perfection in mathematics at the beginning of the 17th century. Because of the extent to which Einsteinian theory was grounded historically on Newtonian science, the Principia had retained its unique seminal position in the history of physics in our post-Newtonian era. Perhaps more strikingly, because of the logical relationship between Newtonian and Einsteinian theory, Einstein showed that Newtonian gravity holds as a limit case in general relativity in just the way Newton showed that Galilean uniform gravity holds as a limit case of inverse square gravity. Even though the Principia can no longer be regarded as exemplar of perfection, it is still widely regarded by physicists as an exemplar of empirical science at its best. In spite of the extravagant claims made about the Principia by some in the years after it first appeared, he seems to have exhausted his argument and left little to be done by those that shall succeed him. The most positive view of it that anyone could have substantiated during the first half of the 18th century would have emphasized its promise more than its achievement. The theory of gravity had too many loose ends, and the most glaring of which was the factor of two discrepancy in the mean motion of the lunar apogee, a discrepancy that undercut the claim that the moon is held in orbit by an inverse square force. No one knew those loose ends better than Newton himself, yet no one had a greater sense of the potential of the theory of gravity to resolve a whole host of questions in planetary astronomy, which may well explain why he made those loose ends difficult to see except by the most technically skilled, careful readers. By the late 1730s and the early 1750s, the situation changed dramatically when several of the loose ends were tied up, in some cases yielding such extraordinary results as the first truly successful descriptive account of the motion of the moon in the history of astronomy. During the second half of the 18th century, the promise of the Principia was not only universally recognized by those active in empirical research, but a large fraction of the promise was realized. What we now call the Newtonian mechanics emerged in the process, as did the gravity-based accounts of the often substantial divergence of the planet from Keplerian motion, the achievement of Newton's theory of gravity that ultimately ended all opposition to it. Yeah, God bless. Last. During the 18th century, the Principia was also seen as putting forward a worldview directly in opposition to the broadly Cartesian worldview that in many circles had taken over from the scholastic worldview during the second half of the 17th century. Newton clearly intended the work to be viewed in this way when in 1686 he changed its title to Philosophiae Naturalis Principia Mathematica, its allusion to Descartes' most prominent work at the time, Principia Philosophiae. The title page of Newton's first edition underscored the illusion by placing the first and third words of the title in larger type. The main difference in the worldview in Newton's Principia was to rid the celestial space of vortices carrying the planets. Newtonians subsequently went beyond Newton in enhancing this worldview in various ways, including forces everywhere expressing the acting at a distance. The clockwork universe aspect of the Newtonian worldview, for example, is not to be found in the Principia. It was added by Laplace late in the 18th century, after the success of the theory of gravity in accounting for a complex derivation from Keplerian motion became fully evident. In addition to viewing the theory of gravity as potentially transforming orbital astronomy, Newton saw the Principia as illustrating a new way of doing natural philosophy. One aspect of this new way, announced in the preface of the first edition, was the focus on forces. For the whole difficulty of philosophy seems to be the discover the forces of nature from the phenomenon of motions, and then to demonstrate the other phenomenon from these forces. It is to these ends that the general proposition in books 1 and 2 are directed, while in book 3, our explication of the system of the world illustrates these propositions. For in book 3, by means of propositions demonstrated mathematically in books 1 and 2, we derive from celestial phenomenon the gravitational forces by which bodies tend towards the sun and towards the individual planets. Then the motion of the planets, the comets, the moon, and the sea are deduced from these forces by propositions that are also mathematical. If only we could derive the other phenomenon of nature from mechanical principles by the same kind of reasoning, for many things lead me to have a suspicion that all phenomena may depend on certain forces by which particles of bodies, by causes not yet known, either are impelled toward one another and cohere in regular figures, or repelled from one another and recede. Since these forces are unknown, philosophers are hitherto made trial of nature in vain. But I hope that the principles set down here will shed some light on either side of this mode of philosophizing, or some truer one. The second aspect of this new method concerns the use of mathematical theory, not to derive testable conclusions from hypotheses as Galilei and Huygens had done, but to cover the full range of alternative theoretical possibilities, enabling the empirical world then to select among them. This new approach is spelled out most forcefully at the end of Book 1, Section 11. I use the word attraction here in a general sense for any endeavor, whatever of bodies, to approach one another, whether that endeavor occurs as the result of the actions of the bodies either drawn towards one another or acting on one another by means of spirits emitted, or whether it arises from the action of ether or the air or any medium whatsoever, whether corporeal or incorporeal, in any way impelling towards one another the bodies floating therein. I use the word impulse in the same general sense, considering in this treatise not the species of focus and their physical qualities, but the quantities in mathematical proportions. As I explained in the definitions, mathematics requires an investigation of those quantities of forces and the proportions that follow from any conditions that may be supposed. Then coming down to physics, those proportions must be compared with the phenomenon so that it may be found out which conditions of forces apply to each kind of attracting bodies. And then finally, it will be possible to argue more securely concerning the physical species, physical causes, and physical proportions of these forces. A third aspect of this new method, which proved most controversial at the time, was the willingness to hold questions about the mechanism through which forces affect their changes in motion in abeyance, even when the mathematical theory of the species and proportions of the forces seemed to leave no alternative but action at a distance. This aspect remained somewhat tacit in the first edition, but then in response to the criticism it received was made polemically explicit in the general scholium added to the end of the second edition. I have not as yet been able to deduce from phenomenon the reason for the properties of gravity, and I do not feign hypothesis, for whatever is not deduced from the phenomenon must be called a hypothesis, and hypotheses, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy. In this experimental philosophy, propositions are deduced from the phenomenon and are made general by induction. The impenetrability, mobility, and impetus of bodies and the laws of motion and laws of gravity have been found by this method, and it is enough that gravity should really exist and should act according to the laws we have set forth, and should suffice for all the motions of the heavenly bodies and of our sea. During most of the 18th century, the primary challenge of the Principia presented to philosophers revolved around what to make of mathematical theory of forces in the absence of a mechanism, other than action at a distance, through which these forces work. By the last decades of the century, however, little room remained for questioning whether gravity does act according to the laws that Newton had set forth and does suffice for all the motions of the heavenly bodies and of our sea. No one could deny that science has emerged that, at least in certain respects, so far exceeded anything that had ever gone before it, that it still stood alone as the ultimate exemplar of science generally. The challenge to the philosophers then became one of spelling out first the precise nature of the limits of knowledge obtained in this science, and then how methodologically this extraordinary advance had been achieved, with a view to enabling other areas of inquiry to follow suit. The historical context of the Principia. The view is commonplace that what Newton did was to put forward a theory of gravity to explain Kepler's already established laws of orbital motion, and the universality of the law of gravity then ended up explaining the derivation from Keplerian motion by attributing them to gravitational interactions of the planets. This is wrong on several counts, the most immediate of which is that Kepler's laws were by no means established before the Principia. The rules for calculating orbital motion that Kepler put forward in the first 2 decades of the 17th century had indeed achieved a spectacular gain in accuracy over anything that had came before. Kepler's rules, however, did not yield comparable accuracy for the motion of the moon, and even in the case of the planets, the calculated locations were sometimes off as much as a fourth of the width of the moon. More importantly, By 1680, several other approaches to calculating the orbits had been put forward that achieved the same level of not quite adequate accuracy as Kepler's. In particular, Newton was familiar with 7 different approaches to calculating planetary orbits, all at roughly the same accuracy. Only 2 of these, Kepler and Jeremiah Horrocks, used Kepler's area rule. Planets sweep out equal areas in equal time with respect to the sun to locate planets along their trajectories. Ishmael Bolyai, and following him, Thomas Street, for whose astronomer Carolina Newton first learned orbital astronomy, replaced the aerial rule with a geometric construction. Vincent Wing had adopted still another geometric construction in the late 1660s after having earlier used a point of equal angular motion oscillating about the empty focus of the ellipse, and Nicholas Mercator in 1676 added still a further geometric construction. Of these 6 alternative approaches, only Horrocks and following him Street took Kepler's three-halves power rule. The periods of the planets vary as the square root of the cube of their mean distance from the sun, seriously enough to use the periods rather than positional observations to determine their mean distances. All these approaches followed Kepler in using an ellipse to represent the trajectory. The primary historical reason for this was Kepler's success in predicting the 1631 transit of Mercury across the sun. This, however, does not mean that the ellipse was established as anything more than a mathematically tractable close approximation to the true orbit. In fact, the planetary orbits known then are not all that elliptical. The minor axis of Mercury is only 2% shorter than the major axis. The minor axis of Mars is only 0.4% shorter. And in all other cases, the difference between an ellipse and an eccentric circle was beyond detection. Newton had real grounds for claiming in a letter to Halley in June 1686 a right to the ellipse, remarking that Kepler knew that the orb to be not circular but oval, and guessed it to be elliptical. Entirely independent, the most judicious reader of the first edition of the Principia, Christian Huygens, wrote the following summary of the Principia's achievement in his notebook upon reading the complimentary copy Newton had sent him. The famous Newton had brushed aside all the difficulties together with the Cartesian vortices. He has shown that the planets are retained in their orbits by their gravitation toward the sun, and that the eccentrics necessarily become elliptical. So all 3 of Kepler's rules that came to be called laws after the Principia were known to be nothing more than holding a high approximation when Newton started out on the project in 1684. And the leading issue in orbital astronomy at the time was not why Kepler's rules hold, but rather which, if any, of their comparably accurate different approaches to calculating orbits would be preferred. The distinct possibility of the ellipse being only an approximation of the true trajectory explains the appropriateness of the question Hooke put to Newton in 1679 and Halley put to him again in 1684. What trajectory does a body describe when moving under an inverse square force directed towards the central body? The inverse square part of the question came from combining the mathematical theory of uniform circular motion, which Huygens had published in his Horologium Osculatorium of 1673, which Kepler's three-halves power rule. The force in a string retaining a body in uniform circular orbit varies directly as the radius of the circle and inversely as the square of the period, but the squares of the periods of the planet vary as the cubes of their mean distance, and hence, at least to the first approximation, the forces retaining the planets in their orbit vary inversely with the square of the radii of their nearly circular orbit, but now allow the distance of the orbiting body from the center to vary rather than remaining constant as a circle. What trajectory would result if the force towards the center varies as the inverse square of the distance from the center towards which the force is always directed? The answer is that in the 9-page tract de Muto, Corpian and Gyrum that Newton sent to Halley in November 1684 is an ellipse, provided the velocity is not too high, and if it is, then instead a parabola or a hyperbola, depending on the velocity. The key step in developing this answer is a generalization of uniform circular motion to the case of motion under centripetal force, a term Newton coined from Huygens' centrifugal force, by which he meant the tension in the string keeping the body in a circle. And a key to this step was the discovery that a body moving under the form of a centripetal force always sweeps out equal areas in equal times with respect to the center, so that the appropriate geometrical representation of time for generalizing uniform circular motion is area swept out rather than angle, or arc length. The tract also confirms Kepler's 3/2 power rule, continuing to hold for bodies orbiting its confocal ellipses governed by the inverse square centripetal forces. These were remarkable steps forward at the time, but they and the questions behind them form only an initial part of the context in which Newton went on to write the Principia. Shortly after De Motu tract went off to London, Newton revised the tract and added two further passages. The questions precipitating this revision appears to have been about the effect the inverse square centripetal forces directed toward Jupiter, as implied by its satellites, have on the Sun. Newton's first added two principles that he called first hypotheses and then changed to laws. Law 3, the relative motion of bodies enclosed in a given space are the same whether that space is at rest or moves perpetually and uniformly in a straight line without circular motion. Law 4, the common center of gravity does not alter its state of motion or rest through the mutual actions of bodies. The second of the two added passages concerns motion in resisting media. It provides a context in which to read Book 2 of the Principia. The first added passage, which had become known as the Copernican Scholium, we here quote in full because it, better than anything else, explains why Newton, into the further research that turned the 9-page tract into the 500-page Principia. It occurs at a single long paragraph, but is here broken into three segments in order to facilitate commenting on it. However, the whole space of the planetary heavens is either at rest, as commonly believed, or uniformly moved in a straight line, and similarly, the common center of gravity of the planets by Law 4 is either at rest or is moved at the same time. In either case, the motions of the planet amongst themselves by Law 3 takes place in the same manner, and their common center of gravity is at rest with respect to the whole space, and so it ought to be considered the immobile center of the whole planetary system. Thence, indeed, the Copernican system is proved a priori, for if a common center of gravity is computed for any position of the planets, this either lies in the body of the sun or will always be very near it. But by season of the deviation of the sun from the center of gravity, the centripetal force does not always tend to the immobile center, and hence the planets neither move exactly in ellipses nor revolve twice in the same orbit. Each time the planet revolves, it traces a fresh orbit, as happens also with the motion of the moon, and each orbit depends upon the combined motions of all planets, not to mention their actions upon each other. Unless I'm much mistaken, it would exceed the force of human wit to consider so many causes of motion at the same time, and to define the motions by exact laws which would allow an easy calculation. Leaving aside these fine points, the simple orbit that is meant that the mean between all vagaries will be the ellipse that I have discussed already. If anyone shall attempt to determine this ellipse by trigonometrical computation from three observations as usual, he will be proceeding without due caution, for these observations will share in the very small irregular motions here neglected, and so cause the ellipse to deviate somewhat from its actual magnitude and position, which ought to be the mean among all errors. And so there will be as many ellipses differing from each other as there are trios of observations employed. Very many observations must therefore be joined together and assigned to a single operation, which mutually moderate each other and display the mean ellipse both as regards position and magnitude. The first segment highlights a further component of the historical context in which the Principia was written and read. Galileo's discovery of the phases of Venus in 1613 had provided decisive evidence against Ptolemaic system, but it could not provide grounds favoring a Copernican over a Tychonian system. It was in the latter, Mercury, Venus, Mars, Jupiter, and Saturn circumnavigate the Sun, and the Sun circumnavigates the Earth, with the consequence that the seven bodies are at times in the same position in relation to one another as are in the Copernican system. Whether any decisive empirical grounds could be found favoring the Copernican over the Tychonian system became one of the most celebrated issues of the 17th century. Kepler, Galileo, and Descartes all published major works in the first half of the century purporting to resolve this issue. Kepler and Descartes, basing their arguments on the physical mechanisms each had proposed of governing the orbital motion. Nevertheless, the leading observational astronomy over the second half of the century, G.D. Cassini, was a Tychonist. It was in the first segment of the Copernican Scholium, Newton identified the center of gravity of the planetary system as the appropriate point to which all the motion should be referred. The technical issue behind the issue over the two systems and then announces that the centripetal forces identified in the text of Demuto as governing the orbital motion opened the way to establishing a slightly qualified form of the Copernican system. Newton's discovery of the time of this line of reasoning was surely a major factor urging him on to the Principia. The second argument of the Copernican scholium addresses an issue in orbital astronomy that forms still further component in the historical context of the Principia, separate from the question whether Kepler's or some other approach was to be preferred, with the question whether the true motions are significantly more irregular and complicated than the calculated motions in any of these approaches, the complexity of the lunar orbit, and the continuing failure to describe it within the accuracy Kepler had achieved for the planets was one consideration lying behind this question. Another came from Kepler's own finding noted in the preface to his Rudolphine tables, and subsequently supported by others, that the true motions may involve further vagaries as evidenced by apparent changes in the value of orbital elements over time. The most important consideration behind this question, however, came from Descartes' claim that in keeping with the changing motion of the vortices over long periods of time, the orbits are not mathematically perfect and they are continuously changed by the passing of the ages. In the second argument of the quoted scholium, Newton concludes that, in contrast to the ellipse that answered the mathematical questions put to him by Hooke and Haley, the true orbits are not ellipses, but are indeed indefinitely complex. This conclusion is nowhere so forcefully stated in the published Principia, but knowledgeable readers nonetheless saw the work as answering the question whether the true motions are mathematically perfect in the negative. Finally, the second and third segments together not only point out that Keplerian motion is only an approximation of the true motions, but they call attention to the potential pitfalls using the orbits published by Kepler and others as evidence for claims about the planetary system. For example, if the true motions are so complicated, then it's not surprising that all the different calculation approaches were achieving comparable accuracy, for all of them at best hold only approximately. Equally, the success in calculating the orbits could not serve as a basis to argue against Cartesian vortices, for the irregularities entailed by them could not simply be dismissed. The specter raised was the very one Newton had objected to during the controversy over the earlier light and color papers. Too many hypotheses could be made to fit the same data. Worse, the multiplicity of tenable hypotheses was a specter haunting mathematical astronomy as a discipline from the end of the 16th century forward. So the conclusion that calculated orbits can at most be merely approximations would have been seen as raising the possibility that the truth and exactness were beyond the reach of mathematical astronomy. The main reason why the Principia includes so much beyond the Demuto tract is Newton's endeavor to reach conclusions that it claimed to be exact and true in spite of the inordinate complexities of the actual motions. The historical context in which Newton wrote the Principia involved a set of issues that readers of the first edition saw it as addressing. Was Kepler's approach to calculating the orbits or some other to be preferred? Was there some empirical basis for resolving the issue of the Copernican versus the Tychonian system? Were true motions complicated and irregular versus the calculated motions? Can mathematical astronomy be an exact science? No reader of the Principia at the time had the benefit of seeing how Newton had these questions tied together in the Copernican scholium, because it did not appear in print until 200 years later. Nothing, however, brings out more clearly the extent to which the extended scope of the Principia stemmed from Newton's preoccupation with the problem of reaching conclusions that had claimed to be exact from evidence that, by his reckoning, held at best to a high approximation. This is why the Copernican scholium provides the most illuminating context for the reading of the Principia. Equally, its being unknown for so long helps to explain why the Principia has generally been read so simplistically. The three editions of the Principia. Newton originally planned a two-book work, with the first book consisting of propositions mathematically derived from the laws of motion, including a handful concerning motion under resistance forces, and the second book, written and even formatted in the manner of Descartes' Principia, applying these propositions to lay out the system of the world. By the middle of 1686, Newton had switched to a three-book structure, with the second book devoted to motion in resisting media. What appears to have convinced him that this topic required a separate book was the promise of pendulum decay experiments to allow him to measure the variations of resistance forces with velocity. When Hooke raised a priority issue on inverse square forces, Newton dropped the original version of the last book, switching to presenting the system of the world in sequence of mathematically argued propositions, many of which demand far more of the reader than anything in the original version. The original system of the world did appear in print the year after Newton died. No complete text for the original version of Book 1 has ever been found. Newton was disappointed in the critical response to the first edition. The response in England was adulatory, but the failure to note loose ends must have led Newton to doubt how much anyone had mastered the technical details. The leading scientific figure of the continent, Christian Huygens, offered a mixed response to the book in his Discourse on the Cause of Gravity, 1690. On the one hand, he was convinced by Newton's argument that inverse squared terrestrial gravity not only extended to the moon, but is one in kind with the centripetal force holding the planets in orbit. On the other hand, I'm not especially in agreement with the principle that he espouses in the calculation and others, namely that all the small parts that we can imagine in two or more different bodies attract one another or tend to approach each other mutually. This I could not concede because I believe I clearly see that the cause of such an attraction is not explicable either by any principle of mechanics or by the laws of motion, nor am I at all persuaded by the necessity of the mutual attraction of whole bodies, having shown that where there are no earth, bodies would cease to tend towards a center because of what we call their gravity. Others on the continent pressed this complaint even more forcefully. The response that many well have bothered Newton most was the review in the Journal des Savants. The work of Newton is a mechanics the most perfectly that one could imagine, as it is not possible to make demonstrations more precise or more exact than those he gives in his first two books. But one has to confess that one cannot regard these demonstrations otherwise than as only mechanical. Indeed, the author recognizes himself at the end of page 4 and the beginning of page 5 that he has not considered their principles as a physicist, but more as a geometer. In order to make an opus as perfect as possible, Newton has only to give us a physics as exact as his mechanics. He will give it when he substitutes true motions for those that he has supposed. Complicating the matter further was the publication of 1689 of Leibniz's essay on the causes of celestial motion, which offered a vortex theory in which a planet moves with a double motion composed of the harmonic calculation of its fluid different orb and the paracentric motion, if it had a certain gravity of attraction, namely an impulsion towards the sun. Leibniz further concluded that when a body is carried in an ellipse or another conic section with a harmonic circulation, at the center both of attraction and of circulation is at the focus of the ellipse, then the attraction or solicitations of gravity will be directly as the squares of the circulation, or inversely as the squares of the radii or the distances from the focus. So within a year and a half of its publication of the Principia, a competing vortex theory of Keplerian motion had appeared that was consistent with Newton's conclusion that the centripetal forces in Keplerian motions were inverse square, thus gave Newton reason to sharpen the argument in the Principia against vortices. The second edition first appeared in 1713, 26 years after the first. It had 5 substantive changes of note. First, the structural argument for universal gravity at the beginning of Book 3 was made more evident, and the word hypothesis was dropped from it. Second, because of the disappointment with pendulum decay experiments and an erroneous claim about the rate of liquid flows vertically through a hole in the bottom of a container, the second half of section 7 of Book 2 was entirely replaced, ending with a new vertical fall experiments to measure resistance forces versus velocity and forcefully stated projection of all vortex theory. Third, the treatment of variations of the surface gravity with latitude was significantly extended, partly in response to Huygens' alternative treatment of the variation, but also because of more recent data from near the equator. Fourth, the treatment of the wobble of the Earth producing the precessions of the equinox was revised in order to accommodate a much reduced gravitational force of the moon on the Earth than in the first edition. Fifth, several further examples of comments were added at the end of Book 3, taking advantage of Halley's effort on the topic during the intervening years. In addition to these, 2 changes were made that there was more polemic than substantive. Newton added the general scholium following Book 3 in the second edition, and his editor Roderick Coates provided a long anti-Cartesian and anti-Leibnizian preface. The third edition appeared in 1726, 39 years after the first, Most changes involved either refinement or new data. The most significant revision of substance was the variations of surface gravity with latitude, where Newton now concluded that the data showed that the Earth has a uniform density. Subsequent editions and translations have been based on the third edition. Of particular note is the edition published by two Jesuits, Lesueur and Jacquier, in 1739 to 42, for it contains proposition by proposition commentary, much of it employing the Leibnizian calculus that extends to roughly the same length as the Newton's text. Definitions of absolute space-time and motion. The Principia opens with a section called Definitions. That includes Newton's discussion of absolute space-time and motion. No part of the Principia has received more discussion by philosophers over the 3 centuries since it was published. Unfortunately, however, a tendency not to pay close attention to the text has caused much of the discussion to produce unnecessary confusion. The definitions inform the reader of how key technical terms, all of them designating quantities, are going to be used throughout the Principia. In the process, Newton introduces terms that have remained a part of physics ever since, such as mass, inertia, and centripetal force. The emphasis is in every one of the definitions is on how the design quantity is to be measured. As illustrated in the opening definition, quantity of matter or mass is a measure of matter that arises from its density and volume jointly. Because a primary measure of density was the specific gravity, no circularity arises here. Newton distinguishes amongst 3 ways of quantifying centripetal forces: the absolute quantity, which corresponds to what we would call the field strength of a central force field; the accelerative quantity, which is the measure of this force that is proportional to the acceleration generated in a given time; and the motive quantity, which is the measure of the force proportional to what we would call the change in linear momentum in a given time. It is important to recognize that in calling the reference of the defined terms quantities, Newton is assigning them to the ontological category of quantity in Aristotle's sense. Thus, force and motion are quantities that have direction as well as magnitude, and it makes no sense to talk of forces as individuated entities or substances. Newton's laws of motion and the propositions derived from them involve relations among quantities, not among objects, in place of no entity without identity. We have no quantity without definite properties, proportions, and the demand on measurement is to supply values that unequivocally yield an adequate approximation to these definite propositions. Immediately following the 8 definitions in the Scholium on space-time and motion, one source of confusion in the literature of the Scholium is not paying attention to the primary distinction Newton is drawing, which is between absolute true mathematical motion versus relative apparent common motion. The naive distinction between true and apparent motion was, of course, entirely commonplace. Moreover, Newton is scarcely introducing it into astronomy. Ptolemy's principal innovation in orbital astronomy, the so-called bisection of eccentricity, entailed that half of the observed first inequality in the motion of the planets arises from a true variation in speed, and half from only an apparent variation associated with the observer being off-center. Similarly, Copernicus's main point was the second inequality, that is, the observed retrograde motions of the planet involved not true but only apparent motions. And the subsequent issue between the Copernican and Tychonian system concerned whether the observed annual motion of the sun through the zodiac is a true or only an apparent motion of the sun. So what Newton is doing in the Scholium on space and time is not to introduce a new distinction, but to exploit with more care and distinction that had been fundamental to astronomy for centuries. The distinction between absolute true and mathematical and relative apparent and common time and place are the conceptual bases Newton employs in laying out the corresponding distinction for motion. He says, relative apparent and common time is any sensible and external measure of precise or imprecise by duration by motion. Adding a parallel point about absolute space, he points out the distinction between absolute and relative time has long been a part of astronomy, insofar as the astronomers have long introduced corrections via the equation of time to the natural day in order to measure celestial motion on the basis of a truer time. And he raises the possibility of there being no uniform motion by which time may have an exact measure. Absolute motion is defined as a change from one place in absolute space to another, but since these parts of space cannot be seen and cannot be distinguished from one another by our senses, we use sensible measures in their stead, adding, it is possible that there is no body truly at rest to which places and motions may be referred. In short, both absolute time and absolute location are quantities that cannot themselves be observed, but instead have to be inferred from measures of relative time and location, and these measures are always only provisional. That is, they are always open to the possibility of being replaced by some new, still relative measure that is deemed to be better behaved across the variety of phenomenon, in parallel with the way in which sidereal time was deemed to be preferable to solar time. Notice here the express concern with measuring absolute true mathematical time, space, and motion, all of which are identified at the beginning of the scholium as quantities. The scholium that follows the 8 definitions thus continues their concern with measures that will enable values to be assigned to the quantities in question. Newton expressly acknowledges that these measures are what we would now call theory-mediated and provisional. Measurements is the very heart of Principia. It pervades the definitions and scholium on space and time, precisely because the primary point of the section is to spell out, in Howard Stein's words, the empirical content of a set of theoretical notions. Accordingly, while Newton's distinctions between absolute and relative time and space provide a conceptual basis for his explicating his distinctions between absolute and relative motion, absolute time and space cannot enter directly into empirical reasoning insofar as they are not themselves empirically accessible. In other words, the Principia presupposes absolute time and space for purposes of conceptualizing the aim of measurement, but the measurement themselves are always of relative time and space, and the preferred measure are those deemed to be providing the best approximation of the absolute quantities. Newton never presupposes absolute time and space in his empirical reasoning. Motion in the planetary system is referred to the fixed stars, which are provisionally being taken as an appropriate reference for measurement, and sidereal time is provisionally taken as the preferred approximation of absolute time. Moreover, in the corollaries to the laws of motion, Newton specifically renounces the need to worry about absolute versus relative motion in 2 cases. Corollary 5, when bodies are enclosed in a given space, their motions in relation to one another are the same, whether the space is at rest or whether it is moving uniformly straight forward without circular motion. Corollary 6, if bodies are moving in any way whatsoever with respect to one another and are urged by equal accelerative forces along parallel lines, they will all continue to move with respect to one another in the same way that they would if they were not acted on by those forces. So while the Principia presupposes absolute space and time for purposes of conceptualizing absolute motion, the presuppositions underlying all of the empirical reasons about actual motions are philosophically more modest. If absolute space and time cannot serve to distinguish absolute from relative motions, more precisely absolute from relative changes of motion, empirically, then what can? Newton answers the causes which distinguish true motions from the relative motions are the forces impressed upon bodies to generate motion. True motion is neither generated nor changed except by forces impressed upon the moving body itself. The problem then becomes one of distinguishing the forces impressed on the bodies, where forces are quantities, and hence the key issue is whether there are theory-mediated measures of them that yield unequivocal values, in contrast to different measures of the same force that yield different values, the hallmark of relative motion. The famous bucket example that follows is offered as illustrating how forces can be distinguished that will then distinguish between true and apparent motion. The final paragraph in the scholium begins and ends as follows. It is certainly very difficult to find out the true motions of individual bodies and actually to differentiate them from apparent motions, because the parts of the immovable space in which the bodies truly move make no impression on the senses. But the situation is not utterly hopeless, but in what follows, a fuller explanation will be given of how to determine true motions from their causes, effects, and apparent differences, and conversely of how to determine from motions whether true or apparent their causes and effects. For this was the purpose for which I composed the following treatise. What does follow are 2 books of propositions that provide means for inferring forces from motions and motions from forces, and a final book that illustrates how these proportions can be applied to the system of the world, first to identify the forces governing motion in our planetary system, and then to use them to differentiate between certain true and apparent motions of particular interest. In this respect, the empirical content of the theoretical concepts that Newton has explicated in the section called Definitions is inextricably linked with the physical theory presented in the rest of the Principia. The contention that the empirical reasoning in the Principia does not presuppose an unbridled form of absolute time and space should not be taken as suggesting that Newton's theory is free of fundamental assumptions about time and space that have subsequently proved to be problematic. For example, in the case of space, Newton presupposes the geometric structure governing which lines are parallel and what the distance are between the 2 points is 3-dimensional and Euclidean. In the case of time, Newton presupposes that with suitable corrections for such factors as the speed of light, questions about whether two celestial events happen at the same time can in principle always have a definite answer, and the appeal to forces to distinguish real from apparent non-inertial motion presupposes that free fall under gravity can always, at least in principle, be distinguished from the inertial motion. Equally, the contention that the empirical reasoning in the Principia does not presuppose an unbridled form of absolute space should not be taken as denying that Newton invoked absolute space as his mean for conceptualizing true deviations from inertial motion. Corollary 5 to the laws of motion quoted above put him in a position to introduce the notion of inertial frame, but he did not do so, perhaps in part because Corollary 6 showed that even using an inertial frame to define deviations from inertial motion would not suffice. Empirically, nevertheless, the Principia follows astronomical practices of treating celestial motions relative to the fixed stars, and one of its key empirical conclusions is that the fixed stars are at rest with respect to the center of gravity of our planetary system. Newton's laws of motion. The designation law of motion has been used in the philosophical transactions of the Royal Society in the late 1660s for principles governing motion under impact put forward by Christopher Wren, John Wallis, and Christian Huygens. Only the first of the three laws Newton gives in the Principia corresponds to any of these principles, and even the statement of it is distinctly different. Every body preserves in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. This general principle, which following the lead of Newton came to be called the principal law of inertia, had been in print since Pierre Gassendi's De Muto Impressa e Motori Translato of 1641. Newton probably first encountered it in print when he read Descartes' Principia, where it is comprised by his first two laws of nature, and is used immediately to assert that any body which is moving in a circle constantly tends to move away from the center of the circle which it is describing. This is the basis for Descartes concluding that some form of unseen matter, namely the vortices, must be in contact with the planet, for otherwise they would go off in a straight line. It is the first of these three hypotheses for which Huygens develops his theory of falling heavy bodies and their motion in a cycloid in his Horologium Osculatorum of 1673. If there were no gravity, and if the air did not impede the motion of the bodies, then any body will continue in its given motion with uniform velocity in a straight line. Newton had adopted it as hypothesis in the registered version of De Muto, though stated without reference to impressed forces. Every body under the sole action of its innate forces moves uniformly in a straight line indefinitely unless something extraneous hinders it. The striking difference in the formulation of Principia versus the one in De Muto, and for that matter versus all earlier formulations in print, is the reference to impressed forces. In all earlier formulations, any departure from uniform motion in a straight line is implied the existence of material impediment to the motion. In the more abstract formulation in the Principia, the existence of an impressed force is implied, with the question of how this force is affected left open. The modern F equals ma form of Newton's second law nowhere occurs in the edition of the Principia, even though he had seen his second law formulated this way in print during an interval between the second and third editions in Jacob Hermann's Phoronomia in 1716. Instead, it has following formation in all three editions. A change in motion is proportional to the motive force impressed and takes place along a straight line in which the force is impressed. In the body of Principia, this law is applied both to discrete cases in which an instantaneous impulse, such as the from impact, is affecting the change in motion, and to continuously acting cases, such as the change in motion and the continuous deceleration of a body moving in a resisting medium. Newton thus appears to have intended his second law to be neutral between discrete forces, that is what we now call impulses, and continuous forces. His stating the law in terms of proportions rather than equality bypasses what seems to us to be an inconsistency of units in treating the law as neutral between these two. The obvious question with the second law is what Newton means by a change in motion. If he had meant a change in what we call momentum, that is, if he had meant in modern notation change in mv, delta mv, the proper phrasing would have been a change in the quantity of motion. In a passage composed in the early 1690s, when Newton was intending to restructure the Principia, he explained what he meant. In other words, the measure of the change in motion is the distance between the place where the body would have been after a given time had it not been acted on by the force and the place it is after that time. This in keeping with the measure universally used at the time for the strength of the acceleration of surface gravity, namely the distance a body starting from rest falls vertically in the first second. The only special provision that Newton has to make is for non-uniform continuously acting forces, for which, in account with lemma 10, he takes the distance AB to vary at the very beginning of the motion in the squared ratio of the times. In If this way of interpreting the second law seems perverse, keep in mind that the geometric mathematics Newton used in the Principia and others were using before him had no way of representing acceleration as a quantity in its own right. Newton, of course, could have conceptualized acceleration as the second derivative of the distance with respect to time within the framework of symbolic calculus. This is the form in which Jacob Hermann presented the second law in his Phoronomia of 1716 and Euler in the 1740s, but the geometric mathematics used in the Principia offered no way of representing second derivatives. Newton employed curvature, that is, the circle touching a curve, in place of the second derivative with respect to distance throughout the Principia. Hence, it was natural for Newton to stay with the established tradition of using the length of the measure of the change of motion produced by a force, even independently of the advantage of this measure had of allowing the law to cover both discrete and continuously acting forces with a given time taken in the limit of the continuous case. Under this interpretation, Newton's second law would have seemed novel at the time. The consequence of impact was also being interpreted in terms of the distance between where the body would have been after a given time had it not suffered the impact, and where it was after this time following the impact, with the magnitude of the distance depending on the relative bulk of the impacting bodies. Moreover, Huygens' account of the centrifugal force, that is the tension in the string, in uniform circular motion in his Horologium Osculatorium, used the measure for the force, the distance between where the body would have been had it continued in a straight line, and its location on the circle in a limiting small increment of time. And he then added that the tension in the string would also be proportional to the weight of the body. So construed in this indicated way, Newton's second law was novel only in its replacing bulk and weight with mass. In the early stages of his work on the Principia, Newton had identified three logically equivalent alternatives for the third law. The action-reaction principle, he ultimately chose the principle we call conservation of linear momentum, corollary 3 in the Principia, and the principle that the common center of gravity of two or more bodies does not change its state, whether of motion or of rest, as a result of the actions of the bodies upon one another, corollary 4. Huygens has stated that both of these principles follow from his solution for spheres in collision, and the center of gravity principles Newton emphasizes amounts to nothing more than the generalization of the principle of inertia, even though his third law was novel in comparison with these other two. Newton nevertheless chose it and relegated the other two to corollaries. Two things can be said about this choice. First, the third law is a local principle, while the two alternatives to it are global principles, and Newton, unlike those working in mechanics on the continent at the time, generally preferred fundamental principles to be local, perhaps because they pose less of an evidence burden. Second, with the choice of the third law, the three laws all expressly concern impressed forces. The first law authorizes inferences to the presence of an impressed force on a body, the second to its magnitude and direction, and the third to the correlative force on the body producing it. In this regard, Newton's three laws of motion are indeed axioms characterizing impressed force. Real forces, in contrast to such apparent forces as Coriolis force, of which Newton was entirely aware, though of course not under this name, are used for which the third law, as well as the first two, hold, for only by means of the law can real forces, and hence real changes of motion, be distinguished from apparent ones. Newton presented his first two laws as already accepted by mathematicians and confirmed by experiments of many kinds. For the third law, by contrast, he offered a variety of forms of support, including experiment on impact. One important element that had become clear in his discussions of evidence for his third law and also in Corollary 2, is that Newton's impressed force is the same as a static force that has been employed in the theory of equilibrium of devices like the level and balance for some time. Newton is not introducing a novel notion of force, but only extending a familiar notion of force. Indeed, Huygens too had employed this notion of static force when he identified his centrifugal force with the tension in the string or the pressure on the wall retaining an object in circular motion. In explicit analogy with the tension exerted by a heavy body on a string from which it is dangling, Huygens' theory of centrifugal force was going beyond the standard treatment of static forces, only in its inferring the magnitude of the force from the notion of the body in a circle. Newton's innovation beyond Huygens was first to focus not on the force of the string, but on the correlative force on the moving body, and second, to abstract this force away from the mechanism by which it acts on the body. Three steps were involved in passing from the already familiar static forces to the more abstract Newtonian dynamic forces, one by Huygens and two by Newton. The continuity with Huygens' theory of centrifugal forces is important in another respect. In his brief defense of the first two laws of motion, Newton remarks, "What has been demonstrating concerning the times of oscillating pendulums depends on the same first two laws and first two corollaries, and this is supported by daily experience with clocks." In Huygens' Horologium Oscillatorium, the only place any counterpart to the second law surfaces in the theory of centrifugal force and uniform circular motion. The theory Huygens presents extends to conical pendulums, including a conical pendulum clock that he indicates has advantages over simple pendulum clocks. In the 1670s, Newton had used a conical pendulum to confirm Huygens' announced value of the strength of surface gravity as measured by simple cycloidal and small arc circular pendulums. Huygens himself had measured the strength of surface gravity with a canonical pendulum, obtaining the same value to four significant figures as he obtained with a simple pendulum. The precise agreement between these two theory-mediated measures of surface gravity, one of them predicated on Newton's first two laws of motion and the other not, in fact constituted the strongest evidence for the first two laws at the time the Principia was first published. For the simple pendulum measure was known to be stable and accurate into the fourth significant figure, the evidence in hand for the first two laws taken as a basis for measuring forces was thus much stronger than has often been appreciated. Save perhaps for the attribution of the F equals ma form of the second law to the Principia, the most widespread mistake about Newton's three laws of motion is that they alone sufficed for all problems in classical mechanics. Those who developed what we now call Newtonian mechanics during the 18th century at all times appreciated how far from the truth this is. Newton's three laws of motion suffice for problems involving what Euler dubbed point masses. Indeed, once given the forces acting on a point mass, the three laws hold for all point masses, including those that lie within bodies. But the three laws must be supplemented by further principles for a whole host of celebrated problems involving bodies, rigid or otherwise, that are not mere point masses. Perhaps the simplest prominent example at the time was the problem of a small arc circular pendulum with two or more point mass bobs along the string. Huygens had solved this problem in part of his Horologium Oscillatorium entitled The Center of Oscillation, in the process providing the theoretical basis for using added masses to tune pendulum clocks. The reason why Newton's three laws of motion have to be supplemented to solve this problem is easy to see. Consider the case of a pendulum with 2 point masses along the length of a rigid string. The counterpoint mass has the effect of reducing the speed of the inner one versus what it would have had without the outer one, and the inner point mass increases the speed of the outer one. In other words, motion is transferred from the inner one to the outer one along the segment of the string joining them. Once the force transmitted to each point mass along the string is known, Newton's three laws of motion are sufficient to determine the motion, but his three laws are not sufficient to determine what this force transmitted along the string is. Some other principles beyond them is needed to solve the problem. Which principle is to be preferred in solving this problem became a celebrated issue extending across most of the 18th century. Okay, KL, God bless. Okay, 1 second, let me just pour a quick drink. Okay. Book 1 of the Principia. Book 1 develops a mathematical theory of motion under centripetal forces. In keeping with the Euclidean traditions, the propositions mathematically derived from the laws of motion are labeled either as theorems or as problems. The theorems all have the if-then form, enabling them to authorize inferences of their consequences given their antecedents. But then so too does the problems in effect have an if-then logical form. For the geometric style solutions, they provide authorized inferences from given information to unknowns. The best way to think of the derived propositions, therefore, is an inference tickets. As such, the propositions fall into three categories: ones that license conclusions about forces from information about motions, and ones that license conclusions about motions from information about forces, and ones that license conclusions about net forces directed towards whole bodies from information about contributing forces directed towards the individual parts of the bodies. A fundamental contrast between Newton's mathematical theory of motion under centripetal forces and the mathematical theory of motion developed by Galilei and Huygens is that Newton's is generic. Galilei and Huygens examined one kind of force, uniform gravity, with their goal of deriving attestable consequences. Newton's theory covers not only forces that vary as 1 divided by radius squared, for which the Principia is famous, but also forces that vary as r and 1 divided by radius cubed, and even as any arbitrary function of radius. At the end of section 11, he gives a reason quoted earlier. Mathematics requires an investigation of those quantities of forces and their proportions that follow from any conditions that may be supposed. Then coming down to physics, these proportions must be compared with the phenomenon so that it may be found out which conditions of forces apply to each kind of attracting bodies. And then finally, it will be possible to argue more securely concerning the physical species, physical causes, and physical proportions of these forces. He had other reasons as well. The theory of gravity entails that the gravity below the surface of a uniformly dense sphere varies linearly with the distance from the center, and hence to at least a first approximation. This is how gravity varies below the surface of the Earth. Centripetal forces that vary as 1 divided by radius cubed hold if and only if the trajectory is spiral. And given any stationary orbit governed by centripetal forces, superposition of a 1 divided by radius cubed centripetal force will cause the orbit to precess, as is the case of a lunar orbit. Still, Newton's main reason appears to have been the one given in the quotation. If one curious respect that Newton mentions only once in passing, the theory does not cover all conditions that may be supposed. Newton's theory treats centripetal forces that vary only with the distance from the force center, that is, one for which the force of the two bodies equally distant from the center is always the same. It does not treat centripetal forces that vary with theta or zeta, the two angular components of spherical coordinates. This is notable for two reasons. First, the centripetal forces arising from Cartesian vortices would almost certainly have varied with both of these angular components, and hence Newton is tacitly begging a question. Second, as Newton himself realized, as quoted in section 13 of book 1, gravity around a spheroid does not simply vary as 1 divided by radius squared, but must also vary with latitude. From Newton's point of view, therefore, gravity around Jupiter and the Earth, and surely the Sun as well, does not vary as simply as 1 divided by radius squared. This is one of many often ignored cues pointing to the extent to which the evidential reasoning of the Principia has to be more intricate and subtle than was appreciated at the time, or for that matter, even now. Up to the end of section 10, book 1, it considers forces that are directed towards geometric centers rather than bodies. As a consequence, only the first two laws of motion enter into any of the proofs until late in book 1. Even further, as Newton develops the theory to that point, under the accelerative measures of force, only the accelerative measures of force is employed, and hence even mass plays no role. Included in the segment are by far the most widely read parts of book 1, then and now section 2, which deals with centripetal forces generally, in section 3, which develops Newton's fundamental discovery that a body moves in a conic section, sweeping out equal areas in equal times about a focus, if and only if the motion is governed by an inverse square centripetal force directed towards this focus. The stick figure picture of book 1 that results from viewing these two sections as its high point blinds the reader not only to the richness of the theory developed in it, but also to several no less important results derived in the rest of it. The paragraph that opens section 11 announces, up to this point, I've been setting forth the motion of bodies attracted towards an immovable center, such as, however, hardly exist in the natural world. I will now go on to set forth the motion of bodies that attract one another. This section first successfully solves the problem of the motion of two bodies under inverse square mutual attraction. It then turns to the case of more than two bodies, for which Newton can only solve the case of mutual attraction that varies linearly with the distance between bodies. For the inverse square case, Newton gives only the qualitative results, most of them in 22 corollaries to proposition 66 that Newton calls imperfect in the preface to the first edition. All of these corollaries identify qualitative tendencies in the motion of body orbiting a second body and attracted to a third, with the majority of the results directed specifically to the perturbing effects of the sun on the motion of our moon. It is with section 11, then, that the Principia departs from the realm of de motu tract and begins to consider the complexities of the true motions. Section 12 and 13 treat attractive forces between bodies that result from are composed out of centripetal forces between each of the individual microphysical particles forming them. Section 12 treats spherical bodies and section 13 non-spherical bodies. As Newton anticipated, this was part of Book 1 that would arouse the strongest complaints from readers committed to the view that all forces involve contact between bodies. On top of this, nowhere in Book 1 did the mathematics become more demanding than here. These two sections give primary attention to the inverse square forces and forces that vary linearly with distance, but just as earlier in Book 1, some results pertain to forces that vary in other ways, included among which are results pointing to experiments that might differentiate between inverse square and any alternative to it. In the Scholium to proposition 78, Newton singles out the result of this inquiry that he had regarded as the most notable. I've now set forth two major cases of attraction, namely when the centripetal forces decrease in the squared ratio of the distances or increases in the simple ratio of the distances, causing bodies to revolve in conics, and composing centripetal forces of spherical bodies that decrease or increase in proportion to the distance from the center according to the same laws, which is worthy of note. This is one of the few places in the Principia where Newton singles out a result in an aside in this way, that an attracting sphere can be answered as if the mass were concentrating at its center in the case of attractive forces that vary linearly with the distance was not so notable. For, as Newton shows in section 13, in the case of attractive forces, an attracting body always can be treated as if the mass were located at its center of gravity, regardless of shape. The truly notable finding is that it is also true of spheres in the case of inverse square forces. The subsequent results in section 12 and 13 indicate that in the case of all other kinds of centripetal force, the attraction towards a sphere is not the same as an attraction towards its mass concentrated in its center, and even in the inverse square case, the result does not hold for other shapes or for spheres that do not have spherically symmetric density. Although Newton does not expressly single out other results of Book 1, a few deserve comment here. The key that opened the way to Newton's theory of motion under centripetal forces was the discovery of how to generalize to non-circular trajectories the solution that he and Huygens had obtained for the centripetal force in uniform circular motion. Newton's proposition 6 generalizes this result to not necessarily uniform motion under centripetal forces along an arbitrary trajectory in which equal areas are swept out in equal time with respect to S in accordance with proposition 1 of Book 1. With this, the body can be viewed as driven from one instantaneous circle to the next by a component of force tangential to the motion, a component that disappears in the case of uniform circular motion. Newton illustrates the value of proposition 6 with a series of examples, the two most important of which involve motion in an ellipse. This contrast raises an interesting question. What conclusion can be drawn from the case of motion in an ellipse from which the foci are very near the center, and the center of force is not known to be exactly at the focus? Newton clearly noticed this question and supplied the means for answering it in the Scholium that ends section 2. Section 10 includes a philosophically important result that has gone largely unnoticed in the literature on the Principia. Newton's argument that terrestrial gravity extends to the moon depends crucially on Huygens' precise measurement of the strength of surface gravity. This theory-mediated measurement was based on the isochronism of the cycloidal pendulum under uniform gravity directed in parallel lines towards a flat Earth. But gravity is directed towards the center of a nearly spherical Earth along lines that are not parallel to one another, and according to Newton's theory, it is not uniform. So does Huygens measure cease to be valid in the context of the Principia? Newton recognizes this concern and addresses it in Proposition 48 through 52 by extending Huygens' theory of the cycloidal pendulum to cover the hypocycloidal pendulum, that is, the cycloidal path produced when the generating circle rolls along the inside of a sphere instead of along the flat surface. Proposition 52 then shows that such a pendulum, although not isochronous under inverse square centripetal forces, is isochronous under centripetal forces that vary linearly with the distance to the center. Insofar as gravity varies thus linearly below the surface in a uniformly dense sphere, the hypocycloidal pendulum is isochronous up to the surface, and hence it can, in principle, be used to measure the strength of gravity. A corollary to this proposition goes further by pointing out that at the radius of the sphere is increased indefinitely, its surface approaches a plane surface, and the law of the hypocycloidal asymptotically approaches Huygens' law of the cycloidal pendulum. This not only validates Huygens' measurement of surface gravity, but also provides a formula that can be used to determine the error associated with using Huygens' theory rather than the theory of the hypocycloidal pendulum. Thus, what Newton had taken the trouble to do in section 10 is to show that Huygens' theory of pendulums under uniform parallel gravity is a limit case of Newton's theory of pendulums under universal gravity. At the end of section 2, he points out in passing that this limit strategy also captures Galileo's theory of projectile motion. In other words, Newton took the trouble to show that the Galilean Huygensian theory of local motion under the uniform gravity is a particular limit case in the theory of universal gravity, just as Einstein took the trouble to show that Newtonian gravity is a limit case in the theory of gravity of general relativity. Newton's main reason for doing this appears to have been the need to validate a measurement pivotal to the evidential reasoning for universal gravity in Book 3. For a philosophical standpoint, however, what is striking is not merely his recognizing the need, but more so the trouble he went to fulfill it. Section 10 may thus illustrate the best of all that Newton had a clear reason for including everything he chose to include in the Principia. Section 9 includes another often overlooked result that is pivotal to the evidential reasoning for universal gravity. In Book 3, Proposition 45 applies the result on precessing orbits mentioned earlier in the special case of nearly circular orbits, that is, orbits like those of the then known planets and their satellites. This proposition establishes that such orbits under purely centripetal forces are stationary, that is, do not precess if and only if the centripetal governing them is exactly inverse square. It does this by deriving a formula relating to the exponent n in the force law to the angle theta between the point where the orbiting body is furthest from the force center to the point where it is nearest, that is, the apsidal angle. This result is striking in three ways. First, insofar as the cumulative effect on even a very small precession is detectable after several revolutions, this formula turns the rate of precession, 2 theta per revolution, into a sensitive measure of the exponent of the force law. Second, it yields a conditional beyond if the orbit is stationary, then the centripetal force is the inverse square. Namely, if the orbit is nearly stationary, then the centripetal force is nearly inverse square. Using Newton's preferred phrasing, quam proxime, literally most nearly as possible. This latter conditional has an if quam proxime, then quam proxime. For Newton illustrates this by taking the mean precession rate of the lunar orbit, 3 degrees per revolution, to conclude that the exponent for the next centrifugal force acting on the moon is -2 and 4 divided by 243. Third, even when an orbit does precess, once such a fractional departure from the exponent from -2 is shown to result from the perturbing effect of outside bodies, then one can still conclude that the force towards the central body is exactly -2. This is precisely the strategy Newton follows in concluding that the centripetal force of the moon, once a correction is made for the perturbing effects of the sun, is inverse square. This is not the only place in Book 1 where Newton takes the trouble to derive an if quam proxime, then quam proxime version of an exact if-then proposition. Propositions 1 and 2 establish that the motion is governed purely by centripetal forces if and only if equal areas are swept out in equal times. The second and third corollaries of proposition 3 then yield the conclusion that motion is quam proxime governed purely by centripetal forces if and only if equal areas are quam proxime swept out in equal times. Again, after establishing that, Kepler's 3/2 power rule holds exactly for concentrical uniform circular motion if and only if an exact inverse square centripetal force holds across all orbits. He adds the generalization, and universally, if the periodic time is as a power r to the n and the radius r, the centripetal force will inversely be as the power r to the 2n minus 1 of the radius, and conversely. This result holds for non-integer values of n, and hence it yields the further result that the 3/2 power rule holds quam proxime for uniform circular orbits if and only if the centripetal force is quam proxime inverse square. These propositions, which Newton has taken the trouble to show still hold in a quam proxime form, are the best ones he invoked in Book 3 to conclude that the forces retaining bodies in their orbits in our planetary system are all centripetal and inverse square. By contrast, as noted earlier, while the proposition if a Keplerian ellipse exactly, then inverse square exactly is true, the proposition if a Keplerian ellipse quam proxime, then inverse square quam proxime is not true when the eccentricity of the ellipse is not large, as explained by Smith in 2002. A failure to notice these quam proxime forms in Book 1 blinds one to the subtlety of the approximative reasoning Newton employs in Book 3. Book 2 of the Principia. The purpose of Book 2 is to provide a conclusive refutation to the Cartesian idea, adopted as well by Leibniz, that the planets are carried around their orbits by fluid vortices. Newton's main argument, which extends from the beginning of section 1 until the end of section 7, occupies 80% of the book. Book 9, section 9, which ends the book, offers a further parting argument. We best dispense with the second argument before turning to the first. The thrust of the argument in section 9 is that fluid vortices are incompatible with Kepler's Aryan 3/2 power rules. The argument has two shortcomings, both of them recognized by Newton's opponents at the time. First, the entire argument is predicated on the hypothesis that resistance that arises from want of slipperiness of the parts of the fluid is ceteris paribus, proportional to the velocity with which the parts of the fluid are separated from one another. Fluids of this sort are now called Newtonian. The absence of evidence for the hypothesis left Newton's opponents free to adopt other rules for the velocity gradient in the vortex generated around a rotating cylinder or sphere, rules that could undercut his conclusion. Second, his analysis of the vortex generated around a rotating cylinder or spheres involves fundamentally wrong physics. It defines steady state in terms of a balance of forces instead of torques across each shell element comprising the vortex. To use Johann Bernoulli's words from 1730, Newton completely neglects to take into account the action of the lever, the considerations of which, however, is absolutely necessary here, it being obvious that the same force applied along the tangent to the circumference of a large wheel has a greater efficacy for making it turn than it has when applied to the circumference of a smaller radius. This is not the only place in Principia where it is clear that Newton had not thought through the mechanics of angular motion. The argument that carried much more weight at the time it convinced Huygens, for example, is the one that extends across the first 7 sections of the book. The thrust of this argument is clear from its conclusion, as stated more forcefully in the second and third editions than in the first. And even if air, water, quicksilver, and similar fluids by some infinite division of their parts could be subtilized and become infinitely fluid mediums, they would not resist projected balls any the less, for the resistance which the subject of the preceding propositions arises from the inertia of matter, and the inertia of matter is essential to bodies and is always proportional to the quantity of matter by the division of the parts of a fluid. The resistance that arises from the tenacity and the friction of the parts can indeed be diminished, but the quantity of matter is not diminished by the division of its part, and since the quantity of the matter remains the same, its force of inertia, to which the resistance discussed here is always proportional, remains the same. For the resistance to be diminished, the quantity of matter in the space throughout which the bodies must move must be diminished, and therefore the celestial spaces, though through which the globes of the planets and comets move continually in all directions freely and without any sensible diminution of motion, are devoid of any corporeal fluid, except perhaps the very rarest of vapors and rays of light transmitted through those spaces. To reach this conclusion, Newton had only show that one, the inertia of the fluid does not indeed produce a resistance force proportional to its density, a force that is independent of the tenacity that is surface friction, and the friction of the parts that is viscosity of the fluid. Perhaps in part in emulation of this approach, the centripetal forces that appeared to have succeeded so well in books 1 and 3. The approach Newton takes in book 2 is to develop, so far as he can, a generic mathematical theory of motion under resistance forces, and then turn to experimental phenomenon, so that in the words of book 1, it might be found out which conditions of forces apply to different kinds of fluid. The theory in book 1 is generic in that it examines centripetal forces that vary as different functions of the distance from the force center. The theory in book 2 is generic in that it examines motion under resistance forces that vary as the velocity squared, the sum of these two, and ultimately even the sum of 2 or 3 independent contributions, each of which is allowed to vary as any power of velocity whatever. Because Newton's goal was to reach a conclusion about the contribution to the total resistance made by the inertia of the fluid, and he recognized the surface friction and viscosity can contribute to the resistance as well, his empirical problem became one of disaggregating the inertial contribution from the total resistance, that is, the contribution that alone varies with the density of the fluid. Fortunately, because gravitational forces so totally dominate celestial motions, the need to disaggregate different sorts of forces did not arise in book 3. From Newton's point of view, then, the basic problem, assuming that 3 independent mechanisms contribute to total resistance forces, only one of which is proportional to the fluid density, was to find an experimental phenomenon that would allow him to determine the 3 exponents in the following schema, and laws defining the 3 coefficients, or more minimally, at least the variation of the coefficient of the last term for the specific case of spheres. Some preliminary pendulum decay experiments showed promise for doing this, leading him in the first edition to rely solely on this phenomenon. The idea was to start a pendulum from several different heights in order to cover a range of velocities, and then to use the simultaneous algebraic equations to fit a 2 or 3 term polynomial to 2 or 3 lost arc data points, changing the exponents until the polynomial achieved good agreement with the other lost arc data points. The theoretical solutions were pendulum motion under resistance forces in section 6 would then allow him to infer the forces from the rate of decay of the pendulum. These theoretical solutions covered resistance forces that vary not only as a velocity to the power 0, 1, and 2, but also to any power at all of velocity. In principle, therefore, he saw himself in position to infer laws for resistance forces on spheres from the phenomenon of a pendulum decay in full parallel with his deduction of the law of universal gravity from the phenomenon of orbital motion in book 3. And he could then conclude from the total absence of signs or resistance forces acting on the planets, and most especially comets, that the density of any fluid in the celestial region must be exactly or very nearly 0. Unfortunately, pendulum decay turned out to not be as well behaved a phenomenon as Newton anticipated it was going to be while he was working the first edition. The problem, as he later realized, was that he had to let the pendulum swing many times in order to measure the rate of decay, and in the process it gave rise to a to and fro motion in the surrounding fluid, so that the relative velocity between the bob and the fluid, which is the velocity that matters in resistance, could not be determined or controlled. The general scholium following section 6 reports detailed decay rate data for an impressive range of experiments, including different sized bobs in air and bobs moving, as well as in water and mercury. The reader is also shown in detail how to proceed from the data in each case to a polynomial as above, defining the resistance force. Any reader who worked through the data discovered what Newton knew, but was less than candid about. No polynomial fit the data. The experiments did not clearly indicate the resistance forces involved no power velocity greater than 2, and they provided good evidence that a velocity squared effect was dominant, even to the extent of masking any effect involving some other power. Newton also managed to extract some highly qualified evidence that the velocity squared effect varies as the density of the fluid and the frontal area, that is the square of the diameter of spheres. This approach to resistance in the first edition relied entirely on pendulum decay experiments. The disappointing evidence that yielded led to a far weaker statement of the conclusion about the absence of fluid in the celestial regions of the first edition than the conclusion of the subsequent edition quoted above. Not long after the first edition was published, Newton initiated some vertical fall experiments in water that persuaded him that the phenomenon of vertical fall in resisting media would yield much better behaved data in the second and third editions. Therefore, even though the pendulum decay experiments are still fully reported, the central argument in Book 2 relies on vertical fall experiments, including ones from the top of the dome of the newly completed St. Paul's Cathedral, to establish a resistance effect on spheres that is proportional to the density of the fluid, the square of the diameter, and the square of the velocity. The data from these experiments were very good, indeed even better than Newton realized, for small vagaries in them that he dismissed as experimental error were in fact not vagaries at all, but evidence that no polynomial of the sort he was seeking is adequate for resistance forces. While the vertical fall experiments put Newton in a position to make his concluding rejection of vortex theory more forceful, they also posed a methodological complication. The vertical fall experiments offered no way of disaggregating the contribution to resistance made by the inertia of the medium from the total resistance, but the argument against vortices required him to show that no matter how perfectly free of friction and viscosity the celestial fluid might be, its inertia would still give rise to resistance forces that would affect the motions of the comets, if not planets as well. From the resistance measured in the pendulum decay experiments, Newton could conclude that the forces in air and water are dominated by a contribution that varies as the velocity squared. If the vertical fall experiments in the air and water, the measured forces varied to first approximation of the product of the density and the velocity squared, but only to a first approximation, leaving room to question whether a purely inertial contribution had been isolated. Newton dealt with this problem by offering a rather ad hoc theoretical derivation for the purely inertial contribution, showing how closely it agreed with the vertical fall results, and proposing that the differences between the theoretical and the measured resistance could be used to investigate other contributions. Success of such program in characterizing the contributions made by surface friction and the viscosity would have provided compelling support for Newton's theory of inertial contribution. Still, the approach left Newton with not so straightforward a derivation of the laws of resistance forces from phenomenon as he had hoped for in the first edition. In fact, there is a deep mistake in Newton's approach to resistance forces that came to be understood only at the beginning of the 20th century. Resistance forces do not arise from independent contributions made by such factors as the viscosity and inertia of the fluid. Consequently, no polynomial consists of a few always positive terms and powers of velocity can ever be adequate for resistance forces. The first indication of this came when D'Alembert, unhappy with Newton's ad hoc theory for the inertial contribution, analyzed the flow of what we now call the perfect fluid about spheres and bodies and of other shapes, discovering in all cases that the net force of the fluid is exactly zero. Consequently, contrary to Newton, there is no such thing as the contribution made to resistance purely by the inertia of the fluid. Resistance forces always arise from a combination of viscous and inertial effects, however low the viscosity of the fluid may be. Newton's assumption that resistance forces can be represented as a sum, one term of which gives the contribution made purely by the inertia of the fluid, was wrong empirically. Much of his assumptions about simultaneity and space being Euclidean turned out to be wrong. Unlike the latter assumptions, however, the assumption about the resistance amounted to a dead end. All of Newton achieved in Book 2 with resistance forces was merely a curve fit. Book 3 of the Principia. Save for short opening sections, Regulae Philosophiae and Phenomena, Book 3, in contrast to Book 1 and 2, is not marked off into sections. Nevertheless, the main body of it does consist of four clearly separate parts: the derivation of the law of gravity, propositions 1 to 8, implications for this law for orbital and rotating bodies from the corollaries to proposition 8 through proposition 24, a quantitative derivation of select lunar inequalities in the precession of the equinoxes from the law of gravities, proposition 25 to 39, and a solution for comet trajectories with examples and comments, proposition 40 to 42. These parts will be discussed in sequence below. Newton's first two rules of reasoning appeared in the first edition. They're labeled as hypotheses. The third rule was added in the second edition, and the fourth rule in the third edition. These are rules intended to govern evidential reasoning in natural philosophy, akin to rules of deductive reasoning, except for their very much not guaranteeing true conclusions from true premises. In particular, Rule 2 authorizes the inference from some same effect to same cause, a notorious invalid reference, and Rule 3 authorizes inductive generalization to all bodies universally of those qualities of bodies that belong to all bodies on which experiments can be made. Newton's phrasing carries no suggestion that these rules yield truths or even a high probability of truth. The operative phrase in both rules 3 and 4, for example, is properly translated should be taken, and rule 4 makes the provisional character of the authorized inferences explicit. In experimental philosophy, propositions gathered from phenomenon by induction should be taken to be either exactly or very nearly truth, notwithstanding any contrary hypothesis, until yet another phenomenon makes such proposition either more exact or liable to exceptions. The philosophical question why Newton's rules are appropriate is best addressed not by asking how they increase the probability of truth, but by asking whether there is some strategy in ongoing research for which these rules will both promote further discoveries and safeguard against dead-end garden paths that ultimately require all the supposed discoveries to be discarded. 6 astronomical phenomena are listed and discussed in the section called Phenomenon, most importantly that Mercury, Venus, Mars, Jupiter, and Saturn, and the satellites of the latter two sweep out equal areas and equal times with respect to the central bodies of their respective orbits, and their periods vary as the three-halves power of the mean distance from these bodies. The ellipse, by the way, is not one of the phenomenon. In Phenomenon 3, Newton rules out the Ptolemaic system, just as Galileo had in his dialogue concerning the two chief world systems, by appealing to the phases of Mercury and Venus and their absence in the case of Mars, Jupiter, and Saturn, to conclude that these 5 orbits encircle the Sun. But this phenomenon and all the others are carefully formulated to remain neutral between the Copernican and Tychonian systems. In Phenomenon 4, Boulay's calculated orbits are treated on par with Kepler's, indicating that the phenomenon do not rule out the possibility that Boulay's alternative to the area rule is correct. Phenomenon 6 explicitly grants that the area rule holds only approximately for the Moon, with a further remark indicating that none of the phenomena are being put forward as holding exactly. This point is the way to the most reasonable reading of all the phenomena. They deserve to reasonably high approximation, but not more than that. The observations of the planets and their satellites made by Tycho and others over a finite period of time, roughly between 1570 and the time of Newton's writing. On this way of viewing the phenomenon, they are in no way contentious or problematic. They leave entirely open not only questions about whether any claims concerning orbits made by Kepler and his contemporaries hold exactly, but also questions about whether any of these claims hold even remotely in other eras, past or future. The phenomenon are thus not inconsistent with Descartes' insistence on the motions and are constantly changing. The deduction of the law of universal gravity from the phenomenon in the first 8 propositions of Book 3 has provoked a great deal of controversy in the philosophical literature over the last century or so. At the heart of this controversy is the challenge posed by Pierre Duhem. How can a deduction proceed from premises the planets sweep out equal areas and equal times and their orbits are stationary to a conclusion of the law of gravity and then imply that the premises are false? The planets do not sweep out equal areas and equal times and the orbits are not stationary but instead precess. The answer is simple. Newton's reasoning is approximative. He is using if-then statements that have been shown in Book 1 to hold if quam proxime then quam proxime form to infer conclusions from premises that hold at least quam proxime over a restricted period of time. Of course, this means that the deduction shows only that the conclusions, most notably the law of gravity, holds quam proxime over the restricted period of time for which the premises hold. The rules of reasoning then license the conclusion to be taken exactly without restriction of space or time. The conclusions so taken do indeed then show that the premises hold only quam proxime, not exactly. This conclusion in no way contradicts the premises. Recognizing that Newton's reasoning in approximative answers another complaint about the deduction of universal gravity. Newton invokes the proposition if bodies move uniformly in concentric circular orbits whose periods vary as the 3/2 power of the radii, then the centripetal forces acting on these bodies vary as the inverse square of the radii of the orbits, knowing full well that the observation had established for centuries that the planets do not move uniformly in circular orbits. Newton does indeed invoke this proposition first to conclude in Proposition 1 that in modern parlance there is an inverse square centripetal acceleration field around Jupiter and Saturn, and next to conclude in Proposition 2 that there is an inverse square centripetal acceleration field around the Sun. The orbits of the satellites of Jupiter were then considered to be circular, and hence Newton's inference from the motion was not so problematic. Well, however, the orbits of Venus, Jupiter, and Saturn were considered to be very nearly circular. The motion in them had been known from before Ptolemy to be uniform. Newton expressly concedes that his inference to the inverse square from the 3/2 power rule for the planets is only approximate when In the very next sentence, he remarks, but the second part of the proposition is proved with the greatest exactness from the fact that the aphelia are at rest. The absence of precession, however, can be used to infer the inverse square only for each orbit individually, not a single unified inverse square centripetal accelerating field encompassing all of the orbits. Newton accordingly using the 3/2 rule for circular orbits to establish that an inverse square field holds around the sun to at least a first approximation, and then using the absence of precession of the individual orbits to tighten the approximation. Interpreting Newton's deduction of universal gravity as an exercise in approximative reasoning answers a further complaint of Duhem insofar as the area rule holds only to a high approximation, so too to any number of alternatives to it, such as Boulay's geometric construction. Hence, Newton's deduction begs the question of why the area rule is to be preferred to the alternatives. This question, however, is irrelevant so long as the conclusion remains in the weak form. The law of gravity holds quam proxime from the planets and their satellites over the time period for which the observations have shown the phenomenon to hold quam proxime. The phenomenon really are sufficient to reach the conclusion in this weak form, so the complaint has bite only when the law of gravity is taken to be exact. But there, however, Newton does provide a response to it when he concludes in Proposition 13 and 14 that the planets would describe areas exactly proportional to the times in stationary orbits if the sun were at rest and the remaining planets did not act upon one another. The reason then why the phenomenon for which Newton proceeded in the deduction have claimed to being preferred to alternative to them is that the theory deduced from them when taken to hold exactly identifies circumstances under which the phenomenon would hold exactly, as well that this is the case amounts to a requirement of the deduction from phenomenon. The leap to taking the law of gravity as exact is justified only if it yields circumstances in which the phenomenon from which it was inferred would hold exactly. This analysis of the deduction of universal gravity does not answer two further complaints lodged against it. First, in concluding that the centripetal force acting on the moon is inverse square, Newton grants that the precession of the lunar orbit implies an exponent of 2 and 4 divided by 243 for the force rather than exactly -2, but then claims that the small fraction can be accounted for by the perturbing action of the sun's gravity. By the magnitude of the action of the sun he gives in his proposition 3 is twice the value he later in book 3 indicates is the correct value. The lacuna was not resolved by Alexis Claude Clairaut until 2 decades after Newton died. Second, when Newton invoked the third law of motion in the corollaries to proposition 5, he is tacitly assuming that, for example, Jupiter and the sun are in effect directly interacting. In other words, he is ignoring the alternative favored by Huygens, that some unseen medium is affecting the centripetal force on Jupiter, a medium that can in principle absorb the linear momentum which Newton is assuming is being transferred from the sun. Huygens may well perceive this lacuna, to which Coates explicitly called Newton's attention while he was preparing the second edition. The group of propositions following the deduction of universal gravity gives indication of the evidential strategy that lies behind the leap to taking this law to be exact. Immediately upon concluding the first, that the planets would sweep out equal areas in equal time in exact ellipses, and then that the orbits would be exactly stationary were it not for the gravitational interactions among the planets, Newton calls attention to the easiest to observe deviations from this idealization, and then still mysterious vagaries of the motions of Jupiter and Saturn, which Newton attributes to their gravitational interaction. Because according to this theory, this idealization would hold exactly in the specified circumstances, these and all other deviations must result from further forces not taken into account in the idealized case. Identifying these forces and showing that, according to the theory, they do produce the deviations is a way for ongoing research to marshal continuing evidence to bear on the theory of gravity. To put the point differently, the initial characterization that Newton identified can serve as a starting point for a process of successive approximations that should yield increasingly close arguments with the complex true motions. These idealizations are especially well suited for this purpose precisely because, according to this theory, they would hold exactly where no other force is at work, and hence every derivation from them should be physically telling, and not just, for example, an accidental feature of the curve fit. Pursuit of such a research program of successive approximation promises to yield either further evidence for the theory of gravity when the program is successful, or the exceptions Newton speaks to Rule 4 that require the theory to be revised. On the other results developed in the group of propositions found the deduction of universal gravity The most heralded at the time were the defense of Copernicanism in Proposition 12 and the identification of the cause of the tides in Proposition 24, two topics that Kepler, Galileo, and Descartes had all addressed. Nevertheless, these two propositions that proved most important were 19 and 20, which respectively derived the non-spheroid figure of the Earth and the variation of surface gravity with latitude under the assumption that the density of the Earth is uniform. This is the only passage in the Principia that Newton reworked extensively in both the second and then again the third edition. As Newton was fully aware, and Huygens and few others realized, these are the only results in the Principia that depend on universal gravity, that is, inverse square gravitation directed towards every particle of moving matter forming the Earth, and not merely macroscopic celestial gravity, inverse square gravity directed towards celestial bodies. In his discourse on cause and gravity, Huygens offered an alternative theoretical account for the figure of the Earth and the variation of surface gravity, and he claimed to have evidence confirming it and hence refuting Newton's universal gravity, in part because evidence of the figure of the Earth and the variation of gravity with latitude were accessible in expeditions to the equator. These were the results in the Principia that were the first to receive concerted critical attention during the 1730s and 40s. There was a complication in all this, however. The extremely precise results from both the figure of the Earth and the variations of gravity that Newton tabulated in the second and third editions were based on uniform density, and hence, like the Keplerian motion, represented an idealization, departures from which would point to non-uniformities of density. Not until Clairaut's theory of the figure of the Earth did means become available to calculate the effects of non-uniformities in the density. Propositions 25 through 35 derive quantitative results for the three lunar inequalities: the systematic departure from the area rule called the variation, the 18-year motion of the line of nodes, and the fluctuating inclination of the orbits from the perturbing action of the sun. From all three, Newton starts with the circular orbit, so these two involve departures from an idealization. The values he obtained for the different components of solar perturbing force in Proposition 25 and subsequently as needed were accurate to several significant figures. All three derivations, which are mathematically demanding, were successful in obtaining agreement with the values of the inequalities obtained from observation, especially so the derivation for the recession of the lunar nodes, for which he achieves agreement with the known value to be better than 98%. Newton must have been mystified by the failure of his seemingly parallel derivation of the 9-year precession of the line of apsides to achieve better than 50% agreement. The scholium following Proposition 35 opens with an explanation for the preceding efforts of the lunar inequalities. I wish to show by these computations of the lunar motions that the lunar motions can be computed from their causes by the theory of gravity. Newton never found a way of deriving the precession of the lunar apogee from the theory of gravity, and consequently he never succeeded with a complete gravity-derived account of lunar orbit. The mathematical treatment of the three lunar inequalities nevertheless did provide added support for this theory of gravity. It also introduced the idea of attacking the problem of the true orbit in a sequence of successive approximations by calculating perturbations in motion in an assumed orbit caused by the gravitational action of the sun. This was not only an entirely new approach to the then unsolved problem of simply describing the motion of the moon, an approach that proceeded from the physical cause to the motion. It was also the beginning of the perturbational approach that dominated all the celestial mechanics from the middle of the 18th century until late in the 20th. As difficult as Proposition 25 through 35 were for the readers at the time, and still are for readers now, they crucially promoted for further research on the complicated orbital motions and ultimately supplied overwhelming support for Newton's theory of gravity. It was a real breakthrough when Newton discovered that the gravitational forces of the sun and moon acting on an obliquely spheroid Earth would produce a wobble of the Earth that at least qualitatively could account for the precession of the equinoxes. No physical explanation for this phenomenon had been proposed before. Newton faced a problem, however, in trying to carry out the quantitative derivation of the precession. He knew the magnitude of the gravitational action of the sun and the Earth, but not that of the moon, for he could not obtain the mass of the moon in the way that he had for the sun, Jupiter, and Saturn, insofar as no bodies orbit the moon. Propositions 36 and 7 endeavor to infer the forces of the moon on the Earth from the differences of the heights of the tides when the sun and the moon are in conjunction and in opposition. In the first section, Newton managed to derive a value for the rate of the precession in good agreement with the known value, but during the quarter century between the first and second editions, he concluded that the value he had used for the moon's force, 6 1/3 times the sun's force, was much too large. The derivation of the precession was therefore extensively revised in the second edition, using a new value for the moon's force, 4.4815 times the sun force, still more than a factor of 2 greater than the correct value. In all editions, their derivation in Proposition 39 treated the wobble not directly as the motion of a rigid body, but in analogy with the motion of the lunar nodes. By the standards of our present physics, no part of Book 3 is further off base than Newton's solution for the precession. The phenomenon, however, subsequently provided important evidence for Newton's theory of gravity when D'Alembert in 1749 carried out a successful derivation based on rigid body motion and correct value of the moon's force derived from the then recently discovered phenomenon of the nutation of the Earth. Newton's account for the tides in Proposition 24, 36, and 37 was much heralded not only at the time, but still today. He is nevertheless receiving more credit for this than is due. He did identify solar and lunar gravity as the forces driving the tides, but this is all he did. He ignored the rotation of the Earth, and worse, he considered only the radial component of the solar and lunar gravitational forces in these three propositions. In fact, the radial components of these forces has a very small effect compared to the transradial component, that is, the component perpendicular to the radial component. All of this became clear in the 1770s when Laplace developed the mathematical theory of tidal motion, from which all subsequent work has been preceded. Book 3 ends with a revolutionary analysis of comet trajectories that occupies roughly 1/3 of the total length of the book in all three editions. This analysis was slow in coming. As late as June 1686, Newton wrote, "The third book wants the theory of comets." What made the problem difficult as compared to planet trajectories was the need to work from a smaller number of imprecise one-shot observations made from a moving Earth. The method presented in Principia fits a parabola iteratively to the observations, employing novel finite difference methods that Newton later expanded into full tract in mathematics, Methodus Differentialis. The method presupposes the theory of gravity, first in opting for a parabola, and the second in assuming that the inverse square centripetal forces known from the planets act on comets along their entire trajectory. The text notes that the trajectories may well be ellipses, but the period of return in that case would be the best way of determining the ellipse. The parabola approximates the high curvature of the ellipse with high eccentricity. The proposal that comets may return was novel, but even more revolutionary at the time was the claim that they button hook around the sun, implying that what has sometimes in the past been taken for two distinct comets was really one comet before and one after perihelion. In the first edition, the method was applied only to the comet of 1680 and 81. The results are presented in a 1-foot long diagram on the only fold-out page of the edition. Nothing like this diagram shown in Figure 3 had ever appeared in print before. The diagram continued to appear in the next two editions, though in reduced form, not requiring to fold out in the third. In the second edition, the method was refined and applied as well to the comets of 1664 and 5, 1683 and 1682, reflecting research Halley had carried out and published in the Astronomia Cometica synopsis of 1705. The comet of 1682, now known as Halley's Comet, was singled out as being sufficiently similar in trajectory to the comet of 1607 to warrant the proposal that it returns every 75 years. Added to the third edition was the retrograde comet of 1723, for which Bradley had supplied comparatively accurate observations, and the method correspondingly displays its most impressive success, with no discrepancies between the calculated and observed position exceeding 1 minute of arc in either legitimate or latitude. This suggested that the more exacting the observation entering into the calculation, the more accurate was the method. Because Newton's theory of comet trajectories depended only on the part that the theory of gravity was that was least controversial, the inverse square centripetal accelerations everywhere around the sun, it does not provoke much philosophical resistance. The success of the method provided evidence that these centripetal forces act equally on comets, contrary to Hooke's proposal in Comet of 1678 that comets must consist of a fundamentally different kind of material from the planets insofar as they do not respond to the forces directed toward the sun in the same way. The success of the method also provided strong evidence that inverse square forces towards the sun hold throughout the space surrounding it, for not only do comets traverse the space between the planet orbits, but also their trajectories, in contrast to those of the then known planets, are often highly inclined with respect to the plane of the ecliptic, most of all because the However, the success of the method provided the most compelling evidence against not only Cartesian vortices, but all theories claiming that the planets are carried around the sun by fluid vortices. Corollary 3 to Proposition 39, and all three editions summarize the argument. Hence, also, it is manifest that the heavens are lacking in resistance, for the comets following paths that are oblique and sometimes contrary to the course of the planets move in all directions very freely and preserve their motions for a very long time, even when these are contrary to the course of the planets. This was the argument that convinced Huygens when he read the first edition, and it became all the more compelling, therefore, as the method that was so successful with further comets. The added evidence supplied in the theory of comets highlights a sometimes overlooked aspect of Book 3, the development of evidence for the theory of gravity, and it does not end with the deduction of the laws of universal gravity at the beginning, but continues all the way through the book. During the 18th century, attention focused overwhelmingly on the evidence supplied by Newton's theory of a figure of the Earth and the variation of surface gravity, the theory of the tides, the quantitative derivation of secular inequalities, the derivation of the precession of the equinox, and the theory of comets. This suggests that both then and now the deduction of universal gravity should not be read in isolation from the rest of Book 3, but instead the entire book should be seen as offering a sustained evidential argument for the theory. Read this way, in the context of the rest of the book, the deduction is most appropriately viewed as intended to establish universal gravity, but only provisionally as a theory on which further research is to be predicated, research that will continue to bring evidence to bear on the theory. The scientific achievement of the Principia. From Haley's anonymous review of the first edition of the Principia forward, there has been a marked tendency to overstate what the Principia achieved. Glossing over the many loose ends, it left for others to recognize and address. The consequence of this is an equal tendency to distort the context of the enormous advances made in both the mechanical and orbital astronomy during the 18th century, diminishing the difficulties those following Newton faced in their accomplishments in resolving them. The Principia is peculiar in this regard, for a list of its achievements without mentioning their loose ends overstates what it accomplished, but a list of these loose ends risks understating its extraordinary achievement. In effort to strike a balance, we here list 11 major scientific issues of the time to which Book 3 supplied answers in the sequence listed, the answers and the most important loose ends in the reasoning offered in the evidential arguments for those answers. 1. What physically retains the planets in orbits around the sun and their satellites in orbits around them? Newton's answer: inverse square gravity. One in kind with everyday terrestrial gravity turned on a largely successful suppressed failure to account for more than half of the precession of the lunar orbit. It tacitly assumed interaction between the sun and Jupiter and the other individual planets, and it raised unanswered questions about whether the perihelia of the planetary orbits do or do not precess. 2. How does gravity vary both below and above the surface of the Earth? In absence of confirming data, Newton's answer to a first approximation linearly with distance to the center below the surface and inversely with the square of the distance above it presupposed uniform density in the first part of a spherical Earth with spherically symmetric density in the second, and therefore left open the possibility that gravity is constant near the surface of the Earth, just as Huygens continued to claim in his response to the Principia, citing supporting evidence. 3. What are the relative densities of the planets with respect to one another in the Sun? Newton gives theory-dependent answers for Jupiter, Saturn, and Earth in the corollaries to Proposition 8, but the one for the Earth, even in the third edition, depended on still questionable value for the horizontal solid solar parallax required to determine the distance of the Moon from the Earth in astronomical units, and no corroborating evidence for these answers has emerged, such as from the actions of Jupiter and Saturn on one another. 4. Is there some principled way to resolve the dispute between the Copernican and Tychonic systems and thereby settle the question of the proper center to which all the motions in our planetary system should be referred? Newton's answer: the center of gravity of the system about which the sun circulates at comparatively small distances depended on the assumed applicability of the third law of motion, in claiming that the sun is in motion and the precise location of the center of gravity remained open in the absence of values for the relative masses of Mercury, Venus, and Mars. 5. What are the true motions of the planets after and which, if any, of the schemes for calculating planet locations is to be preferred? Kepler's, or one of the alternatives to it. Newton's answer was not simple. If the sun were at rest and the remaining planets did not act upon one another, their orbits would be elliptical, having the sum of their common focus and they would describe areas proportional to the times, and the aphelia and the nodes would be stationary. The Keplerian system, amended in the manner of the Horrocks to infer mean distances from the periods, is therefore the preferred approximation to the two true motions. The main loose end in this answer was whether the actual motions do deviate from the Keplerian ideal, and if so, whether all the deviations could be attributed to the specific forces, gravitational or otherwise. A further loose end addressed in part of Book 3 was whether the non-Keplerian motion of the moon can be shown not to be a counterexample to Newton's argument in the case of the planets. 6. Is the motion of Jupiter and Saturn aberrant? And if so, what are the inequalities in it and what causes them? Newton answered yes, because they interact gravitationally, and the dominant inequality has a period corresponding to the 19 years between their consecutive conjunctions. The second part of the answer did not appear in the first edition. By the early 1720s, it had become clear that the dominant period of the anomalies of motion between the two planets is not that their time between conjunctions, but something much of a much longer duration, giving rise to the question of what the vagaries actually are and whether they can be truly derived from Jupiter and Saturn's gravitational forces. 7. How, if at all, does the Earth's surface gravity vary with latitude? And how, if at all, does the Earth's figure differ from a sphere? Newton's answer changes from the first to the second to the third edition, but in all cases, vagaries in the cited data raises the question of what the actual variations are. Also, because his idealized theoretical calculations assume uniform density, his answer raises the question whether the density of the Earth is uniform and whether the true figure of the Earth and variation of surface gravity can be reconciled with non-uniformities in density. 8. What precisely is the motion of the moon, and what gives rise to the inequalities in it? Inequalities not observed in the motions of the satellite of Jupiter and Saturn. Newton's answers this second part is the perturbing effect of the sun's gravity, leaving the answer to the first in the form of a promissory note. Work out all the perturbations from solar gravity, and you will have the answer. The major open question was whether the complex motion of the line of the apsides and the inequality known as the evection, the two features for which the Horrocksian cinematic model that Newton had employed in the Scholium to Book 3, Proposition 35, had restored to an old-fashioned epicycle, can be derived from the action of solar gravity. 9. What causes the tides, and why do they vary in time as well as place in the way they do? Because Newton's answer, the gravitational action of the sun and the moon, were merely qualitative. Room to question whether the moon attracts the Earth, and if so, by how strong a force, and also left open was the question of how the inertia and viscosity of the seas and the rotation of the Earth affects the tide, a question requiring dynamic analysis of the motions of the seas in response to the solar and lunar gravity. 10. What physically produces the precession of the equinoxes? Newton's derivation of the precession from the gravitational action of the moon and sun raised 3 unresolved questions. What are the correct values of the mass of the moon and the oblateness of the Earth? Is the resulting motion of the Earth really analogous to that of the lunar nodes? How does the varying inclination of the moon affect the calculated motion? And 11. What trajectories do comets describe? Newton's answer is conic sections that can at least be approximated by parabolas in the region in which they are observable, gave way to the question whether the parabolic trajectory works for all comets, and not just the comet of 1980-81 in the case of the first edition, and the 3 others analyzed in the second, and the edition 01 in the third. The Principia also left open the question about how the gravity of Jupiter and Saturn might affect the comet motions, whether any significance should be attached to the residual discrepancies between the theory and observation of Newton's results, and which, if any, comets do return in some regular fashion. Careful reading of the Principia makes clear that, although forthcoming about any of the loose ends, Newton was perfectly aware of them all in one way or another, flagging each for the benefit of a highly astute reader. An instructive way to present the history of the 18th century research in the wake of the Principia is to trace how each of these loose ends becomes a prominent matter of concern and was then resolved, at least to the point of being removed as in any way a threat to Newton's theory of gravity. This process of addressing the loose ends in Book 3 did not get underway until 1730, after Newton had died. During his lifetime, the most pressing complaint against the Principia was the absence of a mechanism to account for its action save for action at a distance, which Newton himself regarded as so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. The absence of mechanism, however, was not something that Newton himself regarded as a loose end in the Principia, for he insisted that all the conclusions listed above could be established and any loose ends in them resolved through the law of universal gravity alone, independently of the mechanism responsible for it. Over the decades after he died, those engaged in research predicated on his theory of gravity came increasingly to the same view of the question of mechanism. And finally, the methodology of the Principia. The two passages that remained word for word the same in all three editions of Newton announced that the Principia was meant to illustrate a new approach to empirical inquiry. Neither the remark about deriving forces from phenomenon of motion and then motions from these forces in the preface to the first edition, nor the remark about comparing a generic mathematical theory of centripetal forces with the phenomenon in order to find out which conditions of force actually hold at the end of Book 1, Section 11, however, shed much light on just what this new approach is supposed to be. Other than these two passages, the only notable remark about methodology is the famous passage quoted earlier from the General Scholium added to the second edition as a final parting statement. I have not as yet been able to deduce from phenomenon the reason for these properties of gravity, and I do not feign hypothesis, for whatever is not deduced from the phenomenon must be called a hypothesis, and hypotheses, whether metaphysical or physical, or based on occult qualities or mechanical, have no place in experimental philosophy. In this experimental philosophy, propositions are deduced from the phenomenon and are made general by induction. The impenetrability, mobility, and impetus of bodies and the laws of motion and the law of gravity have all been found by this method. And it is enough that gravity should really exist and should be acting according to the laws that we have set forth and should suffice for the notions of the heavenly bodies and of our sea. Much of the discussion of the methodology of the Principia in the philosophical literature from the 18th century down to the present time has taken this clearly polemical passage as a starting point, generating unfortunately more heat than light. This is not the place to grapple with all the controversy surrounding this passage. Some guarded comments about the methodology of the Principia may nevertheless prove helpful. It is scarcely surprising that the unprecedented success of Newton's theory of gravity stimulated interest in the methodology of the Principia. The obvious thought was to enable this success in other areas by following the same method, but then, even independently of questions about what the method was, one has to consider exactly how it contributed to the success. Viewed in retrospect, Book 2 makes it clear that the question has no simple answer. If Newton followed the same method in Book 2, then the failure of his efforts on resistance forces, even worse, the failure that he did not recognize, show that the method was no guarantee of success. The empirical world must cooperate for it to succeed. Two aspects of the general thrust of the method are perfectly clear. First, Newton viewed it as contrasting with what was then called the method of hypotheses, that is, the method of putting forward hypotheses that reach far beyond the available data and then marshaling evidence for them by deducing testable conclusions from them. Second, Newton viewed the method as requiring the questions he regarded as open when empirical considerations had not yielded answers to them. Whatever may have been required for empirical considerations to establish a theoretical conclusion, and whatever the status provisional or otherwise any such established conclusion was supposed to have. Newton viewed the method as allowing, even mandating, the theoretical answers to some questions could be established even while other closely related questions remained in abeyance. In particular, to use Newton's phrasing from the Scholium that ends section 11, the physical species and physical proportions of forces could, in the appropriate sense, be established even through the questions of their physical causes remain open. The clear aim of the method was accordingly to limit theoretical claims to inductive generalizations as specified by the rules of reasoning of conclusions dictated by experiment and observation. Newton's eschewing the method of hypotheses produced no commentaries at the time. In a manuscript revision of his essays on the causes of celestial motion, Leibniz even adapted Newtonian phrasing. What follows is not based on hypothesis, but is deduced from phenomena by laws of motion. A large fraction of those who had read at most small portions of the Principia and depended on others for their knowledge of its most likely saw Newton as having hypothesized inverse square attraction, and hence as in fact following the method of hypothesis. In the years after Newton died, the most celebrated issues receiving concentrated research arose not from how Newton had arrived at universal gravity, but from the claims he had derived from it concerning the figure of the Earth, the vagaries of the motion of Jupiter and Saturn, and the motions of the Moon. The individuals at the center of the research certainly saw these issues as a test of Newton's theory of gravity, but the distinction between taking the theory as hypothesis and taking it as a provisionally established conclusion was a distinction without much difference for them. Still, it is worth noting that the conclusion Clairaut first draw from the factor of two discrepancy of the motion of the lunar apogee was not that Newton's theory of gravity was false, but that the inverse square needed to be supplemented by a 1 divided by radius to the fourth term, a response fully in keeping with Newton's fourth rule of reasoning. The aspect of Newton's method that did produce controversy at the time was his insisting that he had established conclusions about the physical species and physical proportions of celestial forces while holding questions about their physical cause in advance. This was the core of the complaints by the Cartesians that the Principia was a work of mathematics, not physics. For Newton's two most important critics, however, Huygens and Leibniz, the objection was not to holding the question of physical causes open, but to accepting certain conclusions that in their mind ruled out the very possibility of a proper answer to the question of physical cause. The defect in Newton's method lay in its not imposing the constraint on theory that all action be through contact and not at a distance. The violation of this constraint lay behind Huygens' remarking. Concerning the cause of the tides given by Newton, I am by no means satisfied, nor by all the other theories that he builds upon his principles of attraction, which seems to me absurd. I've already mentioned in the addition to the discourse on gravity, and I've wondered how he could have given himself all the trouble of making such a number of investigations and difficult calculations that have no other foundation than this very principle. This then was the truly controversial aspect of Newton's method in the Principia, with which the next generation had to come to some accommodation before research on its loose ends could become respectable. The idea of developing a mathematical theory in order to enable experiment and observation to provide theory-mediated answers to questions did not originate with the Principia. In his Horologium Oscularium, the work of the Principia most emulates, Huygens had developed a mathematical theory of pendulum motion that enabled measurement of the length of the period of pendulums to provide a robust, precise answer to the question, how far does an object fall in the absence of air resistance in the first second? The measure then of the strength of the surface gravity, and he had developed a mathematical theory of uniform circular motion that enabled measurement of the height and period of conical pendulums to provide a second answer to this question. By the time Newton started on the Principia, pendulums had been in use for more than a decade to answer questions about how surface gravity varies between Paris and other locations. The special problem Newton saw himself as having to face in using mathematical theory to compare a comparable end in the Principia stemmed from his realization expressed in the Copernican scholium that the phenomena of orbital motions are inordinately complicated and hence open to multiple competing descriptions. The problem thus became one finding a way to use mathematical theory to draw definite, robust answers to questions about the physical species and the proportions of forces from these phenomena. These answers opened the way to pursuing the true motions in a sequence of successive approximations, in the process of which continued evidence could be brought to bear on the theory, potentially delimiting its exactness and its universal applicability in the manner Newton had noted in his fourth rule of reasoning. Because the Copernican scholium was unknown at the time, the subtleties of the new method Newton followed to get around this problem went largely unnoticed. Needless to say, these comments do not answer the philosophically most interesting questions of how the method of the Principia contributed to the unprecedented success of its theory of gravity. Hopefully, however, they do remove some sources of confusion that have distorted so much of the philosophical discussion of the Principia. Okay, so there you have 2 hours of an overview of the Principia, one of the most important books in all of history of man. Newton's Principia, a lot of that was extremely tedious and tough to know what to make of. It's important in the history and the development of ideas, and so I'm just going to have to leave it there and go on to David Hume. So this one will be more straightforward because the history of science and reading books that aren't the most moderate in understanding of science is more difficult than philosophy and metaphysics. But so I'm just going to leave it there and continue because I've already I'm already been at it for many hours, and yesterday also I didn't plan on streaming today, but I wanted to get through this, so hopefully I'll finish this in less than 2 hours, and then maybe we'll have some concluding comments and continue on with the research. Okay, so yesterday we looked at Newton's overview of his philosophy, and then a deep dive into the nature of space and time and motion, from Newtonian concepts, absolute space, from the historical concepts and the differences between Cartesian and Leibnizian space-time and motion. And then we looked at a complete overview of the Principia, and now we're going to look at David Hume and his continuation of Newton's thought, and mostly in the development of causation empiricism, because David Hume is more the modern version of the important understanding of the empirical method, empiricism applied to philosophy in general, which was an adaptation to Newton. Although Hume is a critic of Newton, he's one of his best students. So I think Hume and Newton maybe met. So we have Hume is the author of a treatise on human nature, an inquiry concerning human understanding, an inquiry concerning the principles of morals, the history of England from the invasion of Julius Caesar to the Revolution of 1688, and other works. And one of the things here is going to be an abstraction of Newton's concept of cause and effect. And when we look at Descartes, we do the deep dive into Leibniz. We'll see also the Leibnizian conception of cause, and sometimes the principle of sufficient reason could be related to the law of cause and effect, but the concept of cause and effect is possibly the single most concept out of metaphysics. And we saw like conspiracy theory. Conspiracy theory is just an alternative understanding of cause and effect, put to history and modern politics and social science, versus cause and effect for something deep in science. So David Hume is one of the founders of the empirical method being applied to what's called the moral sciences. So this one's also pretty long. Okay, nom, yeah, God forbid. So you just stick with the research. Hume's Newtonianism and Anti-Newtonianism. David Hume's philosophy, especially the positive project of his Science of Man, is often thought to be modeled on Newton's successes in natural philosophy. Hume's self-described experimental method and the resemblance of his rules of reasoning with Newton's are said to be evidence for this position. Hume encourages this view of his project by employing Newtonian metaphors. He talks of an attraction in the mental world on a par with that of the natural world. Hume infers the existence of habits as a kind of mental force, analogous to gravity, the discovery of the principles of association, which in the abstract he calls the most important achievement, are then analogous to the laws of motion. Hume certainly appears to want his readers to feel that he is modeling his project on the successes of natural philosophy exemplified by Newton in the introduction to the treatise, and even more explicitly in the opening pages of Inquiry. Hume suggests that his Science of Man can parallel recent achievements in natural philosophy with rather obvious nods to Newton's success in planetary astronomy. At the start of the Inquiry, he echoes Newton's rejection of hypotheses and restates his allegiance to the experimental method in contrast with his speculative alternative. There is thus no doubt that Hume wants his reader to believe that Newton forms a kind of model. Yet in the totality of Hume's oeuvre, the technical details of Newton's philosophy are rarely discussed explicitly. In fact, some of the most sophisticated analysis of the implication of Newton's philosophy are attributed to Cleanthes, the spokesperson for the inductive argument from design, in the dialogues concerning natural religion. Well, in recent years, many commentators have come to doubt that Philo should be considered a straightforward spokesperson for Hume's view. Few suggest that Hume endorses without qualification Cleanthes' Newtonian argument from design, the foundation of which is undermined throughout Hume's writings. But this raises further complications because Hume can be read as implying that criticism of the design argument can be generated on strictly Newtonian methodological grounds. The authority of experience to which Hume and Newton both appeal does not license an inference supported by analogical reasoning. To a godlike designer of the universe, that would make Hume something of an internal critic of Newtonianism. The same strategy, generally internal criticism to Newtonian natural philosophy, may be thought to operate in Hume's empiricist attack on the putative meaningfulness of invisible or theoretical entities, forces, powers, and masses that made him a favorite of the logical positivists early in the 20th century. This positivist interpretation seemed to go well with Hume's reputation for skepticism. Yet, as positivism gave way to naturalism as the dominant force in the 20th century, Anglophone philosophy, scholarship on Hume has increasingly emphasized the naturalistic element in Hume, while reinterpreting, even downplaying his skeptical tendencies. But if by naturalism one also means that one is willing to accept the authority of science, then one runs into a problem. It is by no means clear that Hume accepts the independent intellectual authority of natural philosophers, including Newton, to have the final word on interpreting Newton's achievements. Before turning to discussion of Hume's relationship to Newton and Newtonianism, one ought to emphasize three problems that beset the scholarly literature on the topic. First, much scholarship on Hume is still surprisingly ahistorical, especially among philosophers. It tends to favor rational reconstruction of arguments over attention to more contextual forms of interpretation. If such philosophers pay attention to the historical figures, these tend to be other canonical philosophers, Descartes, Locke, Mellenbrock, and Berkeley. Second, even scholars that emphasize the historical Hume do not tend to exhibit a working knowledge of the details of Newton's natural philosophy. Nearly all of the literature of this genre, most of it quite careful, compares the details of Hume's philosophy to the evidence from the various textbooks, often Newtonian, potentially available to Hume. Finally, even the most careful and insightful scholarship on Hume tends to ignore the recent scholarly literature generated by the renewed philosophic and historical interest in Newton's philosophy. Hume's evaluation of Newton. This section analyzes Hume's relationship to the public Newton and other early interpreters of Newton as available to Hume. The analysis reveals that Hume is more critical of and less indebted to the core elements of Newton's philosophy than commonly thought. A benefit of this analysis is that many interpretive debates over how to understand Hume's philosophy can be reformulated clearly with fewer anachronisms. Hume's explicit reflections on Newton's writings and character reveal a more ambivalent picture than commonly thought. Hume shows respect, even admiration for Newton's achievements, but he also expresses reservations. Behind the ambivalence, one can find serious philosophical objections to Newton's life and project. This section looks first at Hume's brief discussions of Newton's life and the achievements, and then analyzes the aims behind Hume's science of man. Okay, Mr. Boston, God bless. Hume does not doubt the longevity of Newton's intellectual achievement. The severe scrutiny which Newton's theory has undergone proceeded not from his countrymen but from foreigners, and if it can overcome the obstacles which it meets with at present in all parts of Europe, it would probably go down triumphant to the latest posterity. But elsewhere, when Hume comments more directly on Newton, there are signs of ambivalence. Were we to distinguish the ranks of men by the genius and capacity more than by their virtues and usefulness to the public, the great philosophers would certainly challenge the first rank and must be placed at the top of humankind. So rare is this character that perhaps there has not as yet been above two in the world who can lay just a claim to at least Galileo. Newton seemed to me so far to excel all the rest. According to Hume, Newton has unusual philosophical talent, yet the back-handed nature of Hume's compliment is unmistaken. Newton's work is not characterized by its virtue. The achievement of Newton's philosophy are not very useful to the rest of mankind. For Hume, there is a moral point of view from which Newton's achievement may seem less than entirely praiseworthy. The ambivalence about Newton is not isolated incident in Hume's writing. In the last volume of the History of England, Hume writes, "In Newton, this island may boast of having produced the greatest and rarest genius that ever rose from the ornament and instruction of the species, from modesty, ignorant of his superiority above the rest of mankind, and thence less careful to accommodate his reasoning and common apprehensions, more anxious to merit than to acquire fame. He was, from these causes, long unknown to the world, but his reputation at last broke out with a luster which scarcely any writer during his own lifetime has ever before obtained. In this passage, Hume singles out Newton as the greatest genius. No mention of Galileo this time. Hume is following Fontenelle's interpretation of Newton as a modest genius not concerned with acquiring fame. But again, Hume's praise is not entirely straightforward. It turns out that part of Newton's achievement is due to his failure to possess two kinds of self-knowledge. Newton did not understand how much smarter he was than others, and Newton did not understand how far removed from ordinary people's concerns his theories were. Hume implies that Newton had been more self-aware and more attuned to the environment in which he was writing. He would have been more likely to adjust his mode of reasoning to public prejudice. On Hume's account, Newton did not properly understand his relationship to his readership, and paradoxically, this partly accounts for Newton's success. It seems not to have occurred to Hume that Newton's mode of presentation, the Principia, was a deliberate one to avoid controversy with those who could not follow its intricate geometric arguments, an intention Newton makes explicit in the introduction to Book 3 of the Principia. Moreover, Hume thinks that in certain other respects, Newton shares the superstitious prejudices of his time. This shows another sense in which Hume's admiration for Newton's genius is limited. While defending the stylistic abilities of King James, Hume comments King James has composed a commentary on the Revelations and proved the Pope to be Antichrist. May not a similar approach be extended to the famous writer Napier and even to Newton at a time when learning was much more advanced than during the reign of James? From the grossness of its superstitions, we may infer the ignorance of an age, but never should pronounce concerning of the folly of an individual from his admitting popular errors, consecrating by the appearance of religion. However, Hume did not doubt Newton's religious sincerity. It is for the same reason I maintain that Newton, Locke, Clarke, being Arians or Socinians, were very sincere in the creed they professed, and I always opposed this argument to some libertines who will need have it that it was impossible, but that these philosophers must have been hypocrites. Thus, Hume has no doubts about the intellectual quality of Newton's achievement. His reservations are moral, even theological in nature. One can distinguish these along a private and public dimension. Hume thinks Newton's life reveals a man with genuine limitations in understanding, let alone transcending himself in his times. Hume calls into question the moral quality of Newton's work because they do not serve the public interest, and they and the Newtonians that follow him are infected with superstitious belief. While Hume's criticism of Newton as a man are revealing of Hume's understanding of what it is to be a philosopher, Hume's criticisms of the purpose behind Newton's project ties directly to the anti-Newtonian aims of Hume's science of man. This project is viewed by many contemporary scholars who emphasize Hume's naturalism as Hume's equivalent of what one today would call cognitive science. While Hume admits that Newton was the greatest genius that ever arose from ornament and his instruction of the species, he is unwilling to acknowledge Newton's virtue or usefulness to the public. Moreover, Newton's project lends cover for gross superstition. Instead, in the introduction to the treatise, Hume offers an ambitious alternative project, his Science of Man. In Enquiries into Human Understanding, he calls it a true metaphysics, which battles abstruse philosophy and metaphysical jargon mixed up with popular superstition. Given Hume's criticism of Newton, he may have Newton in mind here. Hume emphasizes the foundational nature of this project. There's no question of importance whose direct decision is not comprised in the science of man, and there is none which can be decided with any certainty before we become acquainted with that science. And pretending, therefore, to explain the principles of human nature, we in effect propose a complete system of the sciences built on a foundation almost entirely new, and the only one upon which they can stand with any security. The success of Hume's systematic science of man has a positive and negative component. On the positive side, in these four sciences of logic, morals, criticism, and politics, political economy, is comprehended almost everything which it can anyway import us to be acquainted with, or with which can tend either to the improvement or ornament of the human mind. Hume makes it absolutely clear where his priorities are, nor ought we to think that this latter improvement of the sciences of man will do less honor to our native country than the former in natural philosophy, but ought rather to esteem it a greater glory upon account of the greater importance of that science, as well as the necessity it lay under of such a reformation. In short, according to Hume, his science of man is far more valuable than Newton's natural philosophy. This is why Hume ends the introduction to the treatise with the claim that we may hope to establish a science of man which will not be inferior in certainty and will be much superior in utility to any other of human comprehension. Moreover, the content of the science of man reveals that even the very Newtonian sciences of mathematics, natural philosophy, and natural religion are in some measure dependent on the science of man, since they lie under the cognizance of man and are judged by their powers and faculties. For Hume, the science of man is the foundational science because it presupposed to some degree by all the other sciences. The details of Hume's science of man shows the weakness of our ordinary cognitive capacity. At the same time, it offers an argument for staying within the confines of potential ordinary experience. Hume's cognitive science has a normative consequence in that knowledge of it is supposed to reduce the inclination towards intellectual overarching for the practitioner of mitigated skepticism. Be tempted to go beyond common life so long as they considered the imperfection of those faculties which they employ, their narrow reach, and their inaccurate operations. Hume's science of man constrains the extent of our theorizing. In subsequent sections, it will be illustrated how Hume reinterprets the limits and content of the Newtonian natural philosophy in light of the science of man or true metaphysics. Hume's scientific education. There is surprisingly little direct evidence of Hume's knowledge of Newton's text. Most of it is circumstantial. Recent archival and careful hermeneutic research by Michael Barfoot has increased our knowledge of the kind of education in differing elements of natural philosophy Hume would have received as a student in Edinburgh. This usefully supplements what can be gleaned from Hume's writings and letters. While new material may show up one day, four important conclusions follow from his study. First, it is very likely that Hume was exposed to many works in the new natural philosophy, medicine, and mathematics in Europe and Britain. Second, while Hume was a student, Boyle's writings and methodology were emphasized at the University of Edinburgh. It appears that Boyle was favored as the preeminent exemplar of modern natural philosophy because of the theological uses of his form of knowledge in the 18th century natural religion. Given the tenor of the education at Edinburgh and evidence derived from Hume's Aurore, it is likely that Hume had a working knowledge of Boyle's hydrostatics, besides if Hume's project aims to an account of hidden processes underlying observed regularities, as opposed to inductively establishing those regularities, then Hume's project is consistent with much of Boyle's. Second, while at the Jesuit College à la Fletch, 1735 to 37, Hume was certainly exposed to Cartesian and Mellenbrockian ideas, and some of his most influential arguments concerning causation and natural theology had their origin in this intellectual environment. Some commentators have argued that the proper interpretation of Hume's methodology, aspirations, and his account of the mind should spring primarily from the Cartesian and Mellenbrockian context. Third, Hume would have been reasonably familiar with Newton's optics, especially his writings on colors. It is less clear how thorough his working knowledge of it was. However, it is less likely that he was exposed to much of the technical, challenging parts of the Principia. As the catalogue at La Fletch testifies, there were 4 entries directly related to Newton, of which only one, a 1720 French edition of Newton's Optics, but no edition of the Principia, refers to an edition that could have been there during Hume's stay. Moreover, if Hume never read the 3rd edition of the Principia, then this could help explain his lack of interest in Newton's 4th rule of reasoning, which was added to the 3rd edition. Fourth, it remains unclear how proficient Hume became in mathematics. There is a manuscript evidence that he attended George Campbell's extramural lectures on fluxions. These notes require careful study, but Barfoot reports that these manuscripts show little evidence of the application of fluxions to natural philosophy as such. Barfoot is correct to suggest that Hume's treatment of mathematics shows depth to Berkeley's criticisms of Newton. There is less evidence for Barfoot's claim that Hume would have had a working knowledge of the most technical parts of the Principia. It is likely that Hume did get to know the relevant edition of optics already during his years spent at the University of Edinburgh, and may well have been exposed to lectures on it as well, but it is uncertain how reliable his working knowledge of it was. Although in general he was dissatisfied with the university education, at least he found some satisfaction in his natural philosophy class taught by Robert Stewart, a probably more important introduction to the outlook that had spread during the influence of the optics came from Hume's medical reading in relation to his mental breakdown at the age of 18. The most important document of the struggle is his 1734 letter to a physician, in which the medical description of his condition, as Stewart puts it, seemed to be consciously modeled on George Chines' The English Malady, published in 1733. A similarly likely source is Mandeville's treatise on the hypochondriac and hysteric disease, In his later life, he probably benefited from discussions with philosophical friends and colleagues, most notably with William Cullen and Joseph Black. These discussions, however, came only after the publication of Hume's chief philosophical works. These friendships were indeed philosophical in the sense that they were founded, at least partly, on sympathies for Hume's philosophical project. It should be emphasized, however, that archival evidence may radically change our picture of Hume's formal education and continuing interest in Hume's natural philosophy. In addition to the manuscript mentioned above, known marginal notes in Hume's hand in a copy of Edinburgh Review, where he works in Newtonian natural philosophy, were reviewed, may reveal further evidence about the nature and quality of his response to issues in Newtonian natural philosophy. Hume's Berkeleyan view of Newton's achievement. The History of England, Hume writes that Newton's research methodology is as follows. There flourished during this period a Boyle and a Newton, men who trod with cautious and therefore the more secure steps, the only road which leads to true philosophy. Newton is cautious in admitting no principle but such as were founded on experiment, but resolute to adopt every such principle, however new or unusual. While this is rather terse, Hume calls attention to three important elements of Newton's natural philosophy: Newton's commitment to an experimental method, the cautious nature of Newton's methodology, Newton's boldness once experience have established a principle. In 18th century terminology, a principle is akin to what we would call a law or fundamental causal explanation. In order to avoid misunderstanding, Hume equates Newton's methodology with Boyle's only on the first 2 points, not the third. Moreover, Hume is aware that Newton rightly rejected Boyle's conception of a mechanism, so Hume admires Newton's methodology and sees it as a source of progress. So for Hume, Newton uses experiment to arrive at explanations. Thus, he seems to echo and accept Newton's claim about hypothesis non fingo. Once such principles or explanations have been arrived at experimentally, Hume sees Newton as adopting them boldly, even if they are unusual or surprising. Hume appears to have assimilated the importance of Newton's third rule of reasoning. Moreover, Hume is discerning the broad outlines of Newton's commitment to the method of analysis and synthesis. But in Hume's account, there is no mention of the importance of mathematics in Newton's methodology. Hume's lack of interest in the aspect of Newton's methodology may be a consequence of his education. Nevertheless, Hume's interpretation of the status of principles makes him deviate from Newton's methodology in a fundamental fashion. In the treatise, he uses the science of man to claim it is beyond the reach of human understanding to penetrate into the nature of bodies or explain the secret causes of their operations. He cannot approve of the ambition to go beyond knowing bodies by their external properties. This contradicts the final paragraph of the general scholium of the Principia, where Newton promises a program of research, perhaps inspired by the success of Francis Huxley's electrical experiments, to penetrate into the nature of matter. Although this program was by no means finished by the time of Newton's death, Newton's optical research had revealed, for example, that light has an internal constitution characterized by the properties in it of the distinct homogeneal or uniform kind, which have different degrees of refrangibility. To see why Hume cannot approve going beyond external properties of bodies, let us take a brief detour through some of the core elements of Hume's epistemology. For Hume, we built up our causal theory from experience on particular events. This is an important constraint for Hume because it allows him to ask who has ever perceived an instance of a power or force in action. This is crucial for Hume's attack on theoretical and invisible entities. For Hume, all of our simple ideas are derived from impression. Hume's attack on notions of substance, mode, essence, force, power, self, and of course God all rely on his rhetorically powerful ability to ask to what impressions such notions can be traced. For ideas always represent the objects or impressions from which they are derived. In the scholarly literature, this has become known as the copy principle. If no such objects or impressions are to be found, then one must conclude that such ideas are the product of passions or emotions, a trivial suggestion of the fancy, or some imperfection in the faculties of the mind. The thrust of Hume's account is to make talk of, say, substance of force, power, God, seem either meaningless or restricted to the particular qualities of bodies from which the idea is derived. At best, they have reference to an effect or some other event constantly conjoined with the cause. Hume's science of man will not permit a realist interpretation of forces as real causes. When the sciences talk about forces or powers, these words must be interpreted. According to Hume, words like force and power have at best a reference to an effect in some other event, and force, power, energy, these words, as commonly used, have very loose meanings annexed to them, and their ideas are very uncertain and confused. Hume denies here the fundamental achievement of the Principia, rather he offers a reinterpretation of Newton. This is made very clear in his addition to the treatise. I must, he writes, confine our speculation to the appearances of objects to our senses, without entering into a disquisition concerning their real nature and operations. Hume is willing to grant that Newton has experimentally discovered various principles, but given Hume's aversion to talk of forces, it is likely that he thinks these principles must be understood at best as a means to keep track of the phenomenon. That is, in fact, for Hume, the Newtonian philosophy, rightly understood, nothing is more suitable to that philosophy than a modest skepticism to a certain confession of ignorance in subjects that exceed all human capacity. In context, Hume redescribes the Newtonian commitment to a vacuum. So when elsewhere Hume describes the philosopher Newton, who had determined the laws and forces by which the revolutions of the planets are governed and directed, his language of forces must be interpreted in light of his deflationary commitments. One may think that Hume's use of Newtonian philosophy in the addition to the treatise suggests that Hume had described Newton's natural philosophy as Newton understood it, as understood by Hume, but this is not likely because everywhere elsewhere he writes, it was never the meaning of Sir Isaac Newton to rob second causes of all force or energy, though some of his followers have endeavored to establish that theory upon this authority. A note on Hume's terminology: God is the first cause, second cause are ordinarily finite causes that operate in nature. So first Hume's Newton accepts some real causes in nature. Hume's Newton is neither a skeptic about causation nor an occasionalist. Leibniz has raised the concern in his exchange with Clarke. Second, Hume is careful to distinguish Newton from the Newtonians. Thus, a more likely interpretation is that Hume believes he has offered a prescriptive interpretation of how Newtonian philosophy should be viewed in light of the results of his science of man, which shows the limitations of our cognitive capacity, and his restrictive form of empiricism, which contributes to his modest or mitigated skepticism. Hume may well have thought himself as an internal critic of cautious Newtonian, for Hume and Newton both appeal to the authority of experience. Nevertheless, the copy principle guides how Hume believes how experiment or experience authoritative for Newton as well as Hume should be analyzed. This may be why Hume claims that Boyle and Newton have shown the road to true philosophy, not that they have completed it. One way to understand Hume's science of man is to see it then as the fulfillment of the Newtonian philosophy rightly understood, that is by Hume. While Hume does not match Berkeley's detail in offering arguments or in explaining how to reinterpret Newtonian invisible entities, Hume does not accept that we can know that invisible causal forces operate in largely empty universe as anything other than useful means to track the appearances. In fact, there is no room in Hume's explanatory model for invisible forces acting as causes. This becomes clear if we reflect on a passage that has received intense scrutiny in the context of the problem of induction. We are determined by custom alone to suppose the future comfortable to the past. When I see a billiard ball moving towards another, my mind is immediately carried by habit to the usual effect and anticipate my sight by conceiving the second ball in motion. There is nothing in these objects abstractly considered are and independent of experience which leads me to form any conclusion, and even after I have had experience of many repeated effects of this kind, there is no argument which determines me to suppose that the effect will be comfortable to past experience. The power by which bodies operate are entirely unknown. We perceive only their sensible qualities, for and what reason have we to think that the same powers will always be conjoined with the same sensible qualities? 'Tis not therefore reason, which is the guide of life, but custom, that alone determines the mind in all instances. To suppose the future comfortable to the past, however easy this step may seem, reason would never to all eternity be able to make it. Hume here is calling attention to the terse argument of the treatise. Our interest is in his claim that the powers by which bodies operate are entirely unknown. We perceive only their sensible qualities, and what reason have we to think that the same powers will always be conjoined with the same sensible qualities? In dialectic context, Hume is here presupposing an explanatory model familiar from Locke and Spinoza, Aristotle, and Boyle, in which hidden powers and sensible qualities of an entity are causally responsible for the sensible qualities. So it is completely natural for early modern natural philosophers to say that these sensible qualities express the essence. These hidden powers may be part of the essence of the entity, or as Newton suggests about gravity in the third rule of reasoning, universal qualities of an entity. So Hume implied target accepts something akin to the explanatory model. This is not insignificant because the explanatory model is the main explanatory template of the early modern science. Now, if one accepts the explanatory model, then the problem of induction reveals two related problems. One concerns the connection among sensible qualities, and the other concerns the connection between hidden qualities and the visible qualities. So if one accepts the explanatory model, one might have thought, for example, that routinely, if not exceptionless, conjoining sensible qualities must always presuppose the same combination of hidden and visible qualities that produce them. So one could solve the problem associated with the first problem by an appeal to the hidden qualities. And thinking this, one could in fact appeal to the same effect, same cause principle of the sort Newton articulates in the second rule of reasoning. To the same natural effects, we must, as far as possible, assign the same causes. To be sure, Newton's versions of the rules recognize exception and is clearly regulative as far as possible, and it does not rely on explanatory models. Rather, in Newton, the rule is a direct consequence of the parsimony principle: admit no more cause of natural things than such as are both true and sufficient to explain their appearances. But as Hume discerns, the explanatory model lacks resources to secure anything like the same visible effect, same hidden cause. That's because Hume thinks that there is always a barrier moving from sensible qualities to the structure of hidden qualities. In the literature on Newton, who also rejected the explanatory model, this is called the transduction problem. Since an influential article by McGuire in 1970, Hume makes this point fully explicit in the first inquiry. He has not by all experience acquired any idea of knowledge of the secret power by which the one object produces the other. This is why Hume's philosophy of science is so deflationary. All any science can show is the relation that obtain among visible qualities, and perhaps those that can be represented on an analogy with them. These relations can be grouped together and given names: elasticity, gravitation, cohesion, or parts, communication of motion by impulse, and be treated as causes of the phenomenon, but these names do not signify or explain features of hidden powers. In Hume's philosophy of science, science remains at the surface. Hume made the point explicit in the note added to the treatise. If the Newtonian philosophy be rightly understood, it will be found to mean no more. A vacuum is asserted, that is, bodies are said to be placed after such a manner as to receive bodies betwixt them without impulsion or penetration. The real nature of the position of bodies is unknown. We are only acquainted with its effects on the senses and its power of receiving body. The barrier between visible and hidden quality powers is independent of the more fundamental problem of induction, that even when one grasps in some way the structure of the hidden qualities ordinarily responsible for conjunction of sensible qualities, one cannot feel secure about their presence and role in any claim one makes about sensible qualities. For a different set of hidden qualities may be responsible for an ordinary conjoined set of sensible qualities. Hume here discerns the outline of the problem of multiple realization as a general metaphysical problem, that in addition, nature may change its course and so change the configuration of hidden qualities that produce sensible qualities, means that the main explanatory framework of modern science is without foundation. In what sense was Hume a Newtonian? Experimentalism is often argued in the subtitle of the treatise. Attempts to introduce the experimental method of reasoning into moral science shows Hume's self-conscious debt to Newton. Experiments certainly play an important role in Newton's science, but only after 1712 does Newton refer to his own philosophy as experimental. In general, Newton emphasizes the mathematical nature of his philosophy. He calls attention to this in the full title, The Principia, Mathematical Principles of Natural Philosophy. However, one interprets Hume's experimental method, it is in no sense mathematical. Hume's so-called experiments do not have the tacit logic of Newtonian experiments. They almost never offer measurements, which are very important for Newton's focus on successive approximation. They do not connect a tight mathematical structure. Moreover, by the standards of Newtonian natural velocity, many of Hume's so-called experiments, for all their ingenuity, have a rather simple structure. They're more akin to systematic observations. In fact, this is almost nothing to distinguish Humean experiment from normal daily experience. In Hume, the word experiment seems to be nearly synonymous with experience, which is not uncommon in the period. The interpretation is also suggested by Hume's description of his experiments as being based on a cautious observation of human life. This is why Hume can claim that experimental inference and reasoning concerning the actions of others enters so much into human life that no man well awake is ever a moment without employing it. Even if we allow for some hyperbole, it would betray considerable ignorance to confuse Newton's experimental method with ordinary human experimental inference and reasoning. So it is not so much the production of data that makes Hume's method of experimental rather than his way of processing the data gathered in various forms of experiment. This method can be reconstructed as a version of analysis and synthesis inspired by Newton's optics that begins with a phenomenon from the historical and everyday observation of human behavior and its analysis, proceeds by experiments judiciously collected and compared in order to arrive at analogies among various instances. From the observation of several parallel instances, the products of comparative analysis so conducted on principles of various faculties like perception, imagination, reason, whose interaction results in ideas and impressions causing behaviors, but their contribution can hardly be measured, and the principles of their interaction can hardly be quantified, not even in principle. So their relations cannot be represented in an algebraic way in terms of relations and quantities, so they cannot be mathematized either. Instead, they remain qualitatively different principles of human nature, and the explanation of human phenomena consists in the description of how these principles, with their distinctive characteristics, figure in producing them. These findings are generalized by induction. What I discovered to be true in some instances, I suppose to be in all, and consequently they are fallible, and the account of human nature founded in them may be misconstrued, even if it is sometimes possible to obtain what natural philosophers after Lord Bacon have affected to call the experimentum crucis, or that experiment which points out the right way in any doubt or ambiguity. It is rarely so, therefore, inquiry into moral matters is just as open-ended as inquiry into natural matters, and the cure is the same here as there, pretty much as Newton envisaged. It is a further inquiry, so for Hume, experimental findings can and need to be further refined by methods that rightly belong to the family of Newtonian successive approximations, by exploring exceptions and limitations, or by limiting superfluous conditions in order to identify the efficacious ones. One could see the feature of Hume's method and as anticipating Mill's method of difference as much as resembling Newton's of optics. Skepticism. If our analysis of Hume's science of man In our analysis of Hume's science of man, we have already encountered Hume's claim that we're unable to penetrate into the internal constitution of matter. So, however else Hume's skepticism is understood, and it has been the subject of intense scholarly discussion during the last 3 decades, the science of man has skeptical implications with regard to his interpretation of Newton's philosophy. Hume's evaluation of Newton, an additional source of evidence in understanding the nature of Hume's skepticism. This evidence reveals that in evaluating Newton's achievement, Hume is pessimistic about the extent and possibility of knowledge of nature. It also shows that Hume's rejected important Newtonian standards criteria in evaluating the claims of natural philosophy. In the history of England, Hume wrote, Boyle was a great partisan of the mechanical philosophy, a theory which, by discovering some of the secrets of nature and allowing us to imagine the rest, is so agreeable to the natural vanity and curiosity of man. Well, Newton seemed to draw off the veil from some of the mysteries of nature. He skewed at the same time the imperfections of the mechanical philosophy and thereby restored her ultimate secrets to the obscurity in which they ever did and ever will remain. This quote reveals crucial details about Hume's position in 3 areas: Hume's understanding of the relative merits of Newton's philosophy and the mechanical philosophy of Boyle, Hume's attitude towards criteria of intelligibility, Hume's skepticism. First, Hume treats Newton's account as a refutation of the mechanical philosophy. Yet, well, as we have seen, Hume certainly saw it as part of the road to a true philosophy. He does not view Newton's achievement as a decisive advance in knowledge of nature, but instead a decisive evidence for the claim that nature will remain unknowable in principle. Hume understands Newton's success as a double-edged sword. Even if Newton removed a source of error and or enlarged our knowledge, he did not so at the cost of undermining any hope of establishing what we might call a final theory. Moreover, it is by no means clear whether Newton is willing to accept Newtonian natural philosophy as a form of knowledge. A natural reading of the passage is to conclude that Hume's views on Newton as successfully, to use an anachronistic term, falsifying the mechanicist program. Well, Hume hedges his bets on offering any evaluation of the positive side of Newton's system. Notice also the grudging use of seemed. The way to make sense of Hume's remark on the history of England is that they reveal that he implicitly accepts the mechanist insistence explicitly associated with Boyle that there was the only program that offered the possibility of intelligible explanation. Even if it is in the hands of many of its practitioners, it only offered hope of a post facto rational reconstruction. Hume's treatment of Boyle reveals that he thought it was a good thing Newton falsified the mechanical philosophy. Hume acknowledges that the mechanical philosophy could offer some successful explanation, but he emphasizes that its practitioners were likely to overestimate, on psychological and methodological grounds, its potential. Hume appears to have assimilated Newton's devastating criticism of the mechanical philosophy. Furthermore, the passage in the history of England lends support for a skeptical interpretation of Hume's philosophy. Hume thinks that Newtonian project will enable some knowledge of nature at the cost of keeping a final theory permanently unavailable to human inquiry. Further, earlier Hume had offered a positive account of the explanatory principles knowable to mankind. Elasticity, gravity, cohesion of parts, communication of motion by impulse. These are probably the ultimate causes and principles which we shall discover in nature, and we may esteem ourselves sufficiently happy if, by accurate inquiry and reasoning, we can trace up the particular phenomenon to or near to these general principles. Let's leave aside for the moment the ultimate metaphysical status, the ultimate causes of principles in Hume's thought. He is willing to accept that some limited set of fundamental scientific laws, ultimate causes, and principles are available to human researchers. Hume hedges his bet a bit. Note his use of probably. Moreover, these four principles, are all associated with Newton's project. The mechanical philosophy had only accepted communication of motion by impulse as an explanatory principle. Of course, Hume treats these laws not so much as describing genuine causes or powers of nature, but rather in opposition to Newton's own view, which insisted on the reality of causal nature of forces as a way to keep track of the appearances. Finally, his passage showed that Hume ruled out that we could ever hope to explain the causes of these laws or unify them in some more ultimate principle. Newton would agree he did not know the cause of these laws, but he would treat it as a question open to further research and speculation. In the context of a discussion of the doctrine of occasionalism, Hume shows he is aware of this. Sir Isaac Newton, though some of his followers have taken a different turn of thinking, plainly reject it by substituting the hypothesis of an ether of fluid, not the immediate volition of the deity and the cause of attraction, as the cause of attraction. This quote is revealing in two more ways, besides showing that Hume may have been aware of some of Newton's attempts at articulating mechanisms for the operation of attraction. Hume recognizes that Newton's followers can deviate from Newton. In light of the text of the History of England, quoted at the start of this subsection, it is clear that Hume thinks Newton's laws are not sufficient for explaining all of nature. So, without yet taking a stance on how to interpret Hume's treatment of induction or his account of causation, one can distinguish two further strands of Hume's skepticism. Hume treats Newton as showing conclusively that the domain of possible knowledge will leave parts of nature unknown forever. In particular, this will include the causes behind our fundamental principles, and the combination of the two entailed that Newtonian natural theology, a very popular 18th century intellectual enterprise, is based on shaky foundations. Together with Hume's emphasis on accounting for the phenomenon in his interpretation of Newtonian philosophy, Hume is far removed from Newton's realist ontology of interacting forces. The two further sources for this difference are revealed when we analyze Hume's departure from Newton's account of causation and Newton's rules of reasoning. Fallibilism. One of Hume's great claims to fame is the articulation of what has become known as the problem of induction, or to use language closer to Hume's, the problematic status of inferences. An informal way to express his insight is that no claim to knowledge matters of fact ought to be thought as definitive because all of our inductive reasoning or inferences, we presuppose that the future will be the same as the past, but we can never be certain that the future will be the same as the past because the evidence for our assumption is based on the uniformity of nature in the past. The uniformity of nature is presupposed in our knowledge, but in our belief, it cannot be secured by reason. Infamously, Hume claimed the source of this belief is not reason but habit, and our confidence in it is derived from instinct. While there is ongoing scholarly debate over the extent of Hume's skepticism that followed from this insight, it is less controversial than for Hume's knowledge of matters of fact. Whatever the ultimate status of Hume's thought is always tentative, subject to revision. This is known as fallibilism. While Hume's argument appears unique to him, although elements of it are prefigured in Berkeley and the Dutch Newtonian Wilhelm Gravenstande, The position is anticipated by Newton. Newton's fourth rule of reasoning reads, in experimental philosophy, propositions gathered from phenomenon by induction should be considered either exactly or very nearly true, notwithstanding any contrary hypothesis, until yet other phenomenon make such propositions either more exact or liable to exceptions. The rule is that we should treat well-confirmed propositions as true or nearly true until there are deviations that promote new research, which in turn lead us to refine our original propositions or reject them for new ones. But while one has a theory, one must not be distracted by possible differing explanations for the found regularities until one has empirical reasons. One accepts that theory is true as a means to developing a better theory. As Newton writes in the preface to the Principia, the principles set down here will shed some light on either the mode of philosophizing or some truer one, emphasis added. Thus, Newton accepts the physical inquiry is forward-looking and may be open-ended. Not only its theories may evolve, but also its methods. Rule 4 implicitly accepts that the future may bring surprises and new evidence, and thus anticipates Hume's fallibilistic insights. As commentators on Hume may have noted, this strand of Hume's skepticism is shared by Newton. It is less clear if Hume learned it from Newton because there is no evidence that he was acquainted with Newton's fourth rule of reasoning, added to the third edition of the Principia. There is no equivalent in Hume's rule of reasoning to Newton's fourth rule. In the section of Hume's rules of reasoning, the significance of the absence of an equivalent to Newton's rule 4 in Hume's thought is explored. 1 second. Causation. In section 3, we saw that Hume's rejection of Newtonian forces as real causes. He argues that we must reinterpret forces and powers as being ideas about effects. In that section, no reference to Hume's widely discussed views on causation was made. In this section, Hume's account of causation is analyzed. Given our focus on the Hume-Newton relationship, no stance of the most controversial issue in Hume scholarships are taken, and causes mere psychological regularity, or are they found in nature? However, recall that Hume insists that it was never the meaning of Sir Isaac Newton to rob second causes of all force or energy, though some of his followers may endeavor to establish that theory upon his authority. So Hume's Newton accepts some real causes in nature. Hume's account of causality covers at least 5 related issues: how we acquire an idea of cause, what is meant by cause, how we reason about causes, whether causes are in the mind or in nature, how we could infer the existence of causes. In this section, we explore how Hume's treatment of what we mean by cause illustrates Hume's critical response to and departure from Newton's philosophy. Hume's treatment of causation straightforwardly rejects at least 2 kinds of causes that appear in Newton's philosophy: final causes and simultaneous causes. Moreover, we show that the structure of human causes is deeply indebted to pre-Newtonian mechanical philosophies associated with Boyle. Hume analyzes how our notion of causality, one applying to events that are contiguous, exhibit temporal priority of the cause, and have constant conjunction, is derived from experiencing constant conjunction of objects that produce a union in the imagination. Hume's account is causal in its own terms, that is, his 2 definitions of the meanings of cause are patterned on the chain of events that he links lead people to acquire the idea of cause. Hume's analysis is a fact approximation and unifies what moderns tend to mean by causation. In his hands, a redefinition version of Aristotelian efficient causation is the only kind of causation available for use. There is thus a stipulative quality to Hume's discussion. One of the tacit targets of Hume's approach is Newton, for Hume's treatment of causation rules out the permissibility of Newton's appeal to final causes in the justification of the inductive and probable argument from design in the general scholium of the Principia. We know the deity only by his most wise and excellent contrivances of things and final causes. Moreover, while Hume and Newton both appeal to authority of experience, there are further serious tensions between Hume's account of causation and the contents of Newton's natural philosophy. For Newton, the behavior of the moon in the orbit and that of, say, apples falling to the earth have the same cause, namely the force of gravity or weights towards the earth. This conflicts with the contingency requirement, which Hume considers essential to causation. it is hard to see how contiguity could be made consistent with the universal nature of attraction. The most distinct principal particles of the universe attract each other. The contiguity requirement notably disappears in the inquiries into human understanding. More importantly, according to Newton, the acceleration produced by the exercise of force is simultaneous with that exercise, thus defying temporal priority. Hume claims that temporal priority of the cause is of no great importance, yet it appears explicitly or implicitly throughout his treatment of causation. Be that as it may, Hume explicitly attacks the possibility of an effect being simultaneous with its cause. Finally, there is a fundamental structural similarity between Humean causes and the causes favored by pre-Newtonian mechanical philosophers like Boyle and Huygens. They have the same structure, priority of the cause over the effect, contiguity, and constant conjunctions. Now, to be sure, Hume is aware that Newton decisively refuted the mechanical philosophy's program, which insisted the explanations be cast in terms of the impact of colliding bodies. Hume rejects the ontological and explanatory reductionism of the mechanical philosophy. Hume introduces 8 rules by which to judge of causes and effects, because it is possible for all objects to become causes or effects to each other. This is why Hume's list of ultimate causes and general principles, elasticity, gravity, cohesion of parts, communication of motion by impulse, is more inclusive than the mechanical philosophy would allow. So even if we were to leave aside the controversial question to what degree Hume would allow the existence of our potential knowledge of real causes in nature, his analysis of what we mean by cause is hostile to Newtonian natural philosophy. Hume rules out final and simultaneous causes. The former play only a role in Newton's theology and natural religion, but the latter are an integral part of what we call his science. Rules of reasoning. Consider these passages. The cause and effect must be contiguous in space and time. The cause must be prior to the effect. There must be a constant union betwixt the cause and effects. It is chiefly this quality that constitutes the relation. The same cause always produces the same effect, and the same effect never arises but from the same cause. This principle we derive from experience and is the source of most of our philosophical reasoning. For when by any clear experiment we have discovered the causes or effects of any phenomenon, we immediately extend our observation to every phenomenon of the same kind without waiting for the constant repetition from which the first idea of this relation is derived. There's another principle which hangs upon this, that where several different objects produce the same effect, it must be by means of some quality which we discover common amongst them. For as the like effects imply like causes, we must always ascribe the causation to the circumstances wherein we discover the resemblance. The following principle is founded on the same reason. The difference in the effects of 2 resembling objects must proceed from that particular in which they differ, for as like causes always produce like effects, when in any instance we find one exception to be disappointed, we must conclude that this irregularity proceeds from some difference in the causes. When any object increases or diminishes with the increase or diminution of its cause, it is to be regarded as a compounded effect derived from the union of the several different effects which arise from the several different parts of the cause. The absence or presence of one part of the cause is here supposed to always be attended with the absence or presence of the proportional part of the effect. This constant conjunction sufficiently proves that the one part is the cause of the other. We must, however, beware not to draw such a conclusion from few experiments. A certain degree of heat gives pleasure. If you diminish that heat, the pleasure diminishes, but it does not follow that if you augment beyond a certain degree, the pleasure will likewise augment, for we find that it degenerates into pain. The 8th and last rule I shall take notice of is that an object which exists for any time in its full perfection without any effect is not the sole cause of that effect, but requires to be assisted by some other principle which may forward its influences and operations, for as like effects necessarily follow from like causes, and in a contiguous time and place their separation for a moment shews that these causes are not complete ones. In the treatise, Hume states 8 rules by which to judge of causes and effects. Because it is possible for all objects to become causes or effects to each other, The source of these rules is ambiguous, although they might have been supplied by the natural principles of our understanding. Hume provides no evidence for this. Nevertheless, Hume thinks it's proper to employ them in his reasoning. Earlier in the treatise, he was even more adamant about the regulative character of these rules. We shall afterwards take notice of some general rules by which we ought to regulate our judgment concerning causes and effects, and these rules are formed on the nature of our understanding and our experience of its operation in the judgments we form concerning objects. So while these rules may be derived from reflection on how our minds work, or some may be derived from experience, they prescribe how we should ascribe causes to objects in the world, especially in our most of our philosophical reasoning. But in Hume's definition of a cause, are at the most useful stipulation that helps one identify causal relations. This is not the place to resolve how Hume is entitled to a normative character of these rules. Now we examine these rules and their debt to Newton. The first three rules define what it is to be cause and effect. As we have seen, they must be contiguous in space and time. The cause must be prior to the effect. There must be constant union between cause and effect. With the exception of these first three, Hume's rules of reasoning have a strong resemblance to Newton's four rules for the study of natural philosophy outlined at the start of Book 3 of the Principia, third edition. For example, Hume's fourth rule, the same cause always produces the same effect, and the same effect never arises but from the same cause, is explained by, for when by any clear experiment I have discovered the causes or effects of any phenomenon, I immediately extend our observation to every phenomenon of the same kind. This echoes Newton's second rule of reasoning, especially in its generalizing tendency, which Newton explicitly asserts in his third rule. That is to say, in his fourth rule, Hume makes explicit what is implied by the simplicity of the nature assumption in Newton's first rule, that the same cause always produces the same effect. Also, Hume's fifth rule is an articulation of Newton's first and third rules. Hume's sixth rule is itself an extension of Hume's fifth. Hume's seventh and eighth rules do not directly echo Newton's fourth rule. Hume admits, however, that one should be cautious in applying and extending the seventh rule because one cannot extrapolate from a few experiments. The example Hume offers on the relationship between heat and pleasure pain is about a mental phenomenon. Even so, we think there is an important critical relationship between Hume's Rule 7 and Newtonian gravitation. This relationship is not explicit in this text. It is established by Hume's wording, which closely follows Newton's phrasing in discussing gravity in the Principia in his Book 3, Proposition 7, Corollary 1. Newton describes gravitation as action in which every attraction toward a whole arises from the attractions towards the individual parts. In Rule 7, Hume speaks in these same terms, arguing that quality that increases or diminishes with the increase or diminution of its cause should be regarded as a compound effect, derived from the union of several different effects, which arise from several different parts of the cause. And elsewhere in the treatise, Hume writes explicitly the force of gravitation using just this language, or on the face of it, then Hume's Rule 7 seems to adopt Newtonian language in order to provide an alternative description of the kind of extrapolation involved in establishing Newtonian gravitation. But only the first half of Rule 7 is compatible with Newton's science. In the latter half, Hume turns against Newton, warning against the attempt to draw such a conclusion from a few experiments. Indeed, we know quite well that the effects can vary proportionally within a certain range of experience and yet behave completely differently outside of this range. Hume gives the example of our experience of fire. A certain degree of heat gives pleasure. If you diminish that heat, the pleasure diminishes. But if you do not follow that, but it does not follow that if you augment it beyond a certain degree, the pleasure will likewise augment, for we find that it degenerates into pain. This argument made with respect to heat is no less applicable to the Newtonian force of gravitation, for what appears to be a strictly proportional relationship over a given range of experience can turn into something quite different when one strays from this range. What we have therefore as follows: Newton's Rule 3, which is the basis for the claimed universality of its law of gravitation, is met and replaced by Hume's Rule 7, whose intent is in a certain sense precisely the opposite. The so-called universal law of gravitation must be regarded only as characterizing a certain range of human experience and no more. Extension of this law beyond our experience or beyond what perceptible models allow for, whether into the heavens or in the micro world, cannot be admitted into science except as hypothesis. And the same will have to be said for all the other qualities that are attributed to bodies significantly outside of the bounds of our actual experience. What to Newton is nothing less than the foundation of all natural philosophy, his Rule 3 is in Hume's philosophy shown to be unnecessary for scientific reasoning and of questionable validity. This suggests that is Newton's rule 2, that Hume considers to be Newton's chief rule of philosophizing, an interpretation that fits well with what Hume writes about method in both the treatises and in his later writings. It also reinforces the view that Hume rejects in Rule 3 as being that part of Newton's philosophy that is worthy of being adopted and imitated. Indeed, Hume's point is precisely that it is Newton's Rule 2 chiefly that we should be interested in. Rule 3, with its extravagant claims concerning the presence of supposedly essential qualities in every body in the universal far from common life, is one we can afford to set aside. The view we have presented here is at odds with that of Gracilia de Paris, who builds her discussion of Hume's debt to Newton around Hume's putative embrace of Newton's Rule 3 as the cornerstone for his philosophical method. Hume's eighth rule is, as Hume implies himself, a refinement of Hume's fourth rule. It presents overzealous causal description to an object. In his explanation of the rule, Hume presupposes the spatial and temporal contiguity requirement of cause and effect, but is not an essential feature of the rule. But the first part of it, an object which exists for any time in its full perfection without any effect, appears to target non-Newtonian theology or Spinozic arguments, so will not be discussed here. On Hume's interpretation, Newton's second rule is the only rule that is said to be derived uncontroversially from experience. It is a crucial rule because the fifth and sixth rules are by Hume's light extensions of the fourth. Moreover, the conjunction of Hume's fourth and seventh rule produces a new rule. In effect, always holds proportion with its causes. We call this Hume's ninth rule. If one assumes or prescribes that linear causal relations are the only possible ones, this new rule allows Hume to rule out competing claims that posit the existence of causal relations that are not proportional. Hume can use the rule as a constraint on a theory. It plays a prominent role in Hume's political economy when he rejects mercantilism, and more important for our present purposes, in his criticism of the use of analogy in the Newtonian argument from design. Hume's ninth rule also has Newtonian debts. Since the time of Aristotle, many philosophers have asserted proportionality between cause and effect in one fashion or another. Hume's ninth rule echoes, for instance, a principle Leibniz uses quite frequently, the principle of equality of cause and effect. It is a basis of argument Leibniz gives for his conservation principles, but Leibniz's formulation is in terms of equality, not proportionality. Unlike Leibniz and other Cartesians, Newton preferred to reason in terms of proportionality. Although Hume's ninth rule is not derived from any of Newton's official rules of reasoning, Newton does implicitly use a rule like Hume's ninth throughout the Principia. For example, the importance of the proportion between cause and effect is emphasized throughout the treatment of the behavior of bodies in resisting fluid, which, given the importance for Hume of treating money as a fluid, may have caught Hume's attention. Hume also treats resistance in his footnotes. Moreover, there is a prominent place in the Principia where Newton implicitly transforms a version of Hume's seventh rule into Hume's ninth rule, in which proportionality is emphasized. In the Scholium, Newton starts employing the language and emphasizing the importance of proportionality. This is not ruled out by Newton's own rules, but it was not emphasized there. This passage could have attracted Hume's attention for two reasons. It is one of the few explicit methodological passages in the Principia, and it offers an account into what Newton means by attraction. Hume was almost certainly aware of this passage because the proper meaning of attraction is discussed with explicit appeal to Newton's intention. Hume's footnote, Hume makes the ninth rule explicit and uses it as a constraint with which competing theories in political economy, the argument for design, can be ruled out. Hume's use of it in his attack on the design argument is an instance where Hume attacks Newton with Newtonian tools. Moreover, there are two connected, important further differences between Hume's and Newton's rule. First, Hume never quite endorses the universal reach implied by Newton's third rule. For Newton, we extend the known qualities of bodies within our experiential reach to all bodies in the universe. While it could be compatible with Newton's third rule, Hume's fourth rule does not go that far. There is one instance where Hume appears to accept an implication of Newton's rule. The production of motion by impulse and gravity is a universal law which has hitherto admitted of no exception. Leave aside the fact that this would be, a very puzzling way to express the inverse square law. The context makes clear that Hume has in mind causes that are entirely uniform and constant on Earth, not their universal reach. That is why, in context, his other examples involving the burning of fire and the suffocation of every human creature by water, this is textual support to suspect that Hume would deny the universal scope implied by Newton's third rule. Hume takes maxim in the footnote, which argues against inferring new effects from any cause only known only by its particular effects. This denies Newton's strategy of making ever more audacious inferences about planetary motion, the tides, the shape of the Earth, comets, etc., based on the acceptance of universal gravity. The argument in favor of the maxim reveals the tension with Newton's third rule. To say that the new effects produced only from a continuation of the same energy, which is already known from the first effects, will not remove the difficulty. Forever granting this to be the case, which can seldom be supposed, the very continuation and exertion of a like energy, for it is impossible and can be absolutely the same. I say this exertion of a like energy in a different period of space and time is very arbitrary superstition. Newton's first three rules offers a bold methodological program that attempts to unify science across different periods of space and time. It is a bet on the causal unity of nature. The maxim cautions against overconfidence in this regard. Hume's caution is prophetic because it turns out that the subatomic entities behave very differently than macroscopic bodies. However, it is not entirely certain if one should ascribe the maxim in the footnote to Hume because it is offered in the voice of a friend who is pretending to be Epicurus. Second, Hume lacks an equivalent to Newton's Rule 4. Hume is not alone in ignoring Rule 4. Even Reid and Priestley, who have very much to say about the authority of Newton's rules of reasoning, tend to ignore the fourth rule. Adam Smith seems to have been one of the few 18th century figures to have taken it seriously. Recall that Newton's Rule 4 can be viewed as an encouragement to find and exploit known deviations from the regularities one has established in order to make them more exact. A proposal about how to treat a theory that is as true until proven otherwise. Hume seems to have not appreciated the first point at all. On the second point, we have seen that Hume shares Newton's commitment to fallibilism, but this common commitment also hides an important difference between Hume and Newton, which is connected to the observation just made about the contrast between Newton's third rule and the maxim of the footnote of Hume's. Newton's fallibilism includes commitment to the truth of the propositions within one scientific theory until it is proven to be false. Newton realizes that induction can never be certain for all time. He does anticipate Hume in this respect, but is also an expression of Newton's scientific naturalism. Empirical science is authoritative until one has empirically reason to refine theory. This means that at any time one risks the danger of going beyond one's evidence, but this is the methodological price one must pay to make further progress. In his eagerness to combat Newtonian superstition, Hume is willing to be more cautious. Hume's omission of an equivalent rule has several implications for his philosophy and its relationship to Newton. First, Hume replaces the authority of natural philosophy by his own criterion, the copy principle. When it comes to existence claims, only the idea can be traced to a distinct impression will be permissible. Thus, Hume's science of man, or true philosophy, offers to evaluate the claim of natural philosophy from a privileged position. This is the sense in which Hume is not a scientific naturalist. Second, without a commitment to the truth of scientific theory, Hume has conceptual elbow room for a distinction between the provable experimental claims of common life, including some parts of natural philosophy, and the lesser probable commitment of the more abstract parts of natural philosophy. This, too, is a result of Hume's science of man. Recall that Humean practitioners of mitigated skepticism will not be tempted to go beyond common life so long as they consider the imperfection of those faculties which they employ, their narrow reach, and their inaccurate operations. The distinction between a provable common life and the far less probable parts of natural philosophy runs through all of Hume's major work, yet its implication for Hume's attitudes towards Newtonian natural philosophy are not discussed until the dialogues. There, Cleanthes, the spokesman for the Newtonian natural religion, attacks the Humean position. They are even obliged to acknowledge that the most abstruse and remote objects are those which are best explained by philosophy. Light is in reality anatomized. The true system of the heavenly bodies is discovered and ascertained, but the nourishment of bodies by food is still an inexplicable mystery. The cohesion of the parts of matter is still incomprehensible. In reality, would not a man be ridiculous who pretends to reject Newton's explication of the wonderful phenomenon of the rainbow, because that explication gives a minute anatomy of the rays of the light, a subject, forsooth, too refined for human comprehension? And what would you say to one who, having nothing particular to object to the arguments of Copernicus and Galileo for the motion of the earth, should withhold his assent or the general principle that these subjects were too magnificent and remote to be explained by the narrow, fallacious reason of mankind. In vain would the skeptic make a distinction between the science and common life, or between one science and another. The arguments employed in all, if just, are of a similar nature and contain the same force and evidence. Or if there be any difference among them, the advantage lies entirely on the side of theology and natural religion. Many principles of mechanics are founded on very abstruse reasoning, yet no man who has any pretensions to science, even no speculative skeptic, pretends to entertain the least doubt with regard to them. The Copernican system contains the most surprising paradox and the most contrary to our natural conceptions, to appearances, and to our very senses. Yet even monks and inquisitors are now constrained to withdraw their opposition to it. Cleanthes points out that if philosophy asserts the distinction between common life and science, philosophy would set itself against some of the best supported parts of natural philosophy, which are often most removed from common life. We may naturally think that the sun is in motion, but the reality behind the appearances can be very surprising. Cleanthes' point is that philosophy cannot hope to argue against the authority of science without looking as backward as monks and inquisitors who attacked Copernicanism. For our purposes, there are three important features in Cleanthes' discussion. First, he claims that the same kind of correct reasoning applies to all domains. This is a very popular argument among religious Newtonians like Reid. So just because science deals with uncommon domains and obscure topics, it can still contain just reasoning. This is in fact one of the major assumptions behind Hume's own rules of reasoning. So Cleanthes uses Hume's philosophy to undercut part of Hume's anti-Newtonian strategy. Even if Philo were not bound by Hume's philosophy, and there is no evidence he should be considered as a strict spokesman for Hume, as a defender of the epistemic priority of common life, he has no resources to claim that there is a different, correct form of reasoning for areas beyond common life. Second, if there is debate between science and common life, the advantage is with science. No skeptic who at least pretends to be informed is seriously willing to doubt the results of natural philosophy. That is, by the last third of the 18th century, natural philosophy has an authoritative claim to knowledge, even if it is founded in the very uncommon abstruse principles. Third, Cleanthes assimilates the success of natural philosophy to theological and natural religion. He does not recognize a principled distinction between science and religion. If Philo attacks natural religion, he attacks science itself. Contemporary advocates of intelligent design, who claim that it should be treated as a scientific theory, followed the same strategy as Cleanthes. Initially, it seems that Cleanthes' argument is left without a response, so there appears no room for a principled difference between common life on the one hand and natural philosophy and natural religion on the other hand. In the remainder of the dialogues, Philo makes sure not to be thought of as attacking natural philosophy again, in the context where the intellectual authority of science has become unchallengeable. Philo's best hope lies in driving a wedge between natural philosophy and natural religion. This may explain why, in undermining Newtonian natural religion, Philo does not draw on some core elements of Hume's philosophy, the copy principle, or Hume's attack on the permissibility of final causes. Rather, throughout the dialogues, Philo offers more narrow arguments attacking the content of natural religion. So while in part one of the dialogues, Philo has no immediate response to Cleanthes' argument, later in the dialogues he continues to use some distinction between the secure reasoning available in common life and those too far removed from it. For example, by using Hume's ninth rule, Philo is critical of the use of analogy in making claims about the nature of the first cause. Philo relies on common sense to formulate the problem of evil. If God is all-powerful, then he was responsible for natural and moral evil. At the end of the dialogue, Philo is willing to grant Cleanthes that the cause or causes of order in the universe probably bear some remote analogy to human intelligence. So while Philo is unable to draw a conclusive principled distinction between natural philosophy and natural religion, he reduces the latter to a very minimal thesis. It may, of course, be possible that by the end of his life, Hume had limited his aims to removing the superstitious element of Newtonianism. Perhaps he had given up on claiming the priority of the science of man over natural philosophy, but it would be a mistake to identify the pusillanimous dialogues as Hume's final definitive philosophy. Hume appended an advertisement to the Inquiries Concerning Human Understanding, which was printed at the start of the pusillanimous 1777 edition. After distancing himself to some degree from the juvenile work, the Tristes, he says about the Inquiries Concerning Human Understanding, henceforth the author desires that the following pieces may alone be regarded as containing his philosophical sentiments and principles. The Inquiries Concerning Human Understandings, of course, Hume's copy principle, and the attack on final causes. Perhaps the closing remarks of Philo where he apologizes for intervening in the education and instruction of his pupil, Pamphilus, the official narrator of and witness to the dialogues among Philo, Cleanthes, and Endymion, should be taken more seriously by more of Hume's readers. The dialogues are Hume's efforts to educate the students of natural religion. They are not a statement of Hume's positive science of man or true metaphysics. Okay, Mr. Boston, welcome back. Mathematics. There's been a persistent strain of criticism of David Hume that has insinuated that he simply did not understand Newton or lacked mathematical competence. But when Hume or any other historical figure deviates from Newton, this need not entail lack of understanding. It can, depending on other evidence, be taken as informed criticism. In Hume's case, critical scholars also draw on a 1772 letter to William Strahan, in which he mentions a 1755 draft essay on the metaphysical principles of geometry that he withdrew upon the advice of his friend and mathematician, Lord Stanhope, who convinced me that either there was some defeat in the argument or in its perspicuity. This remark is taken as evidence of Hume's acknowledged lack of confidence in mathematics, but it could also be taken at face value as an expression of scholarly integrity. He accepted a compelling criticism. However far his understanding of complex mathematics reached, he advanced a radical skeptical challenge for mathematicians, and thereby he also undermined knowledge claims associated with demonstrated reasoning. The skeptical problem rises from the inexactness of geometric ideas and the fallibility of our reasoning process. Geometry for Hume is about actual figures and shapes whose ideas cannot be perfectly exact because their perceptual abilities are limited, and reasoning based on these ideas inherits this inexactness. Ideas relevant for arithmetic numbers do not suffer from this imprecision, but arithmetic reasoning is just as fallible as human reasoning in general. The outcome of our demonstrative reasoning must be judged by a probabilistic judgment on the reality of our reasoning faculties, which in turn must be judged by a further probabilistic judgment on the probabilistic judgment of the reliability of our faculties. The apparent demonstrative certainty of our mathematical reasoning degenerates into probability, and when we are left with fallibility and uncertain conclusions, even in our demonstrative sciences. But Hume does not stop there. He offers a skeptical solution to his challenge. First, he offers an individual remedy for the mathematician to go back and check again his reasoning, because every time he runs over his proof, his confidence increases. Secondly, social processes are more effective in reducing doubt because his certainty is increased still more by the approbation of his friends, and his reason to its utmost perfection by the universal assent and applause of the learned world. Even if all demonstrative knowledge remains probabilistic, in this approach too, the certainty of mathematical reasoning reaches its peak due to the acknowledgement of epistemic appearance. The popularity of a mathematical proof or demonstration among experts in the field naturally speaks in favor of the proof. This feature is not peculiar to mathematical conclusions, because as Hume points out, I feel all my opinions loosen and fall of themselves when unsupported by the approbation of others. What makes mathematics peculiar is that, in addition to individual reasoning, the approbation of the mathematician's close circle of friends and the approval of scholarly community seems to be the only source of justification in matters of mathematics. By connecting mathematical certainty to the approbation of others, Hume gives an essentially social character to mathematical knowledge. No matter the different metaphysical and epistemic pedigree of its branches, it is their practices that determine the certainty of mathematical conclusions. In practice, geometric reasoning is elevated to the same level of certainty as our reasoning in arithmetic and algebra, and his may be one way to explain why the inquiry lists all of them as demonstrative. The limitations of our practices arising from human nature condemn all branches of mathematics to eventual fallibility and uncertainty. But that is not the main lesson we should draw here. What really matters is that despite the fallibility we generate certainly throughout our predominantly social practices, so geometry in practice can be certain and demonstrative as arithmetic in principle demonstrated, but in practice fallible. Taken together, the metaphysics and practice of mathematics leads us pretty much the same epistemic grounds in all branches of mathematics. Hume's reservation about the demonstrability of mathematics imply a critique of Newton's program of mathematizing natural philosophy. This criticism is not wholly implicit. Rather, Newton is very clearly the target of remarks made in the context of Hume's discussion of the principle of infinite divisibility in the paragraphs subsequent to the treatise on human nature. We're We are not possessed of any instrument or art of measure which can secure us from all error and uncertainty. We therefore suppose some imaginary standard of equality by which the appearances and measuring are exactly corrected and the figures reduced entirely to that proportion. But though the standard be only imaginary, the fiction, however, is very natural, nor is anything more usual than for the mind to proceed after this manner with any action, even after the reason has ceased, which first determined it to begin. This appears very conspicuously with regard to time, where though 'tis evident we have no exact method of determining the proportions of parts, not even so extant as in extension, yet the various correction of our measures and their different degrees of exactness have given us to obscure and implicit notion of a perfect and entire equality. This the case is the same in many other subjects. A painter forms the same fiction with regard to colors, a mechanic with regard to motion. Instead of introducing certainty into natural philosophy, as Newton claims, mathematics, albeit a useful device, is almost every art in almost every art and profession, is thus grounded in natural fictions. It has a limited contribution to the advancement of knowledge. Mathematics, in Hume's eyes, is only another human cognitive enterprise that has no potential to make other fields of knowledge immune to human fallibility. This is in sharp contrast with the cognitive optimism Newton expresses in the preface to Principia and several other passages about the role of mathematics in natural inquiry. Newton is confident that by making the method of inquiry mathematical, natural philosophy can be infused with certainty and demonstrativity. This confidence is undermined by Hume's account of how mathematical knowledge is possible at all. Analysis and synthesis. What is distinctive about the method in the Principia is what I.B. Cohn termed the Newtonian style. Its constitutive feature is the mathematization of nature, dealing mathematically with the realities of the external world. This means much more than deriving numerical results from experiments or the focus of measurement or a commitment to a means of exposition that proceeds from definitions and axioms. Instead, it meant taking mathematics as the model of reality, constructing the mathematical analog of a natural situation, and then to advance from the idealized case by the addition of further conditions towards more accurate mathematical analogs of actual situations. There's no traces of this approach in Hume. So, if one takes the Principia Newtonian style as the essence of Newton's method, then one should conclude that Hume's experimental method is not Newtonian. As Maguire points out, Newton does not see any dichotomy in method between the one used in Principia and the one found in optics. But even if he considered his methodology fundamentally the same in both works, he treated mathematical and experimental analysis as contributing to inquiry in the same manner. This was perceived differently by subsequent generations. In Curie Theory 1, Newton himself introduces two different ways of analysis that may proceed from compound to ingredients and from motions to forces producing them. The first way allows for qualitative analysis that does not require the centrality of mathematical framework of analysis. The crucial element is indeed common to their methodology, namely the idea of causal analysis that is the core of Newtonian analysis, and these are the terms in which Colin Maclaurin introduces the Newtonian method to his contemporaries. Nevertheless, it is immediately clear from the passage that an analysis from compounds to ingredients must proceed differently and find different causes from an analysis from motions to the forces producing them. This will be different with respects to both the method of analysis and the nature of the causes that can be so analyzed. From the angle of Newton's preface to the first edition of the Principia, the basic problem of philosophy seems to be to discover the forces of nature from the phenomenon of motion and then to demonstrate the other phenomenon from these forces. So its method is focused on analyzing the cause of motions in terms of forces, a quantifiable natural kind that is defined in terms of other quantities. So defined, the problem cries out for a mathematical apparatus, and so it fosters what Cohn termed the Newtonian style in philosophy, taking mathematics as the model of reality, constructing the mathematical analog of a natural situation, and then producing from the idealized case by the addition of further conditions more and more accurate mathematical analogs of actual situations. Through this series of successive approximations, Newton's axioms of the laws of motion function as inference tickets that allow for drawing conclusions from motions to forces and vice versa, and also from macrophysical to microphysical forces composing them. The analysis of compounds to ingredients, followed by in the optics, looks for parts, components, constituents, and accompanies the mathematical methods of analysis, where they prove to be inadequate in themselves. The qualitative component of analysis is intended to reveal the composition of an optical and, especially in the queries, chemical phenomenon. The paradigmatic cases are, of course, Newton's prism experiments that revealed the composition of white light. In the first two books of optics, Newton himself uses the method of analysis of compounds into ingredients to discover and prove the original differences of rays of light. This, that is, to discover qualitative differences that persist due to a lack of their analysis in the Newtonian style, most notably among them, as the experimentum crucis has revealed, are colors that are not qualifications of light derived from refractions or reflections of natural bodies, and 'tis generally believed but original and connate properties which in differ rays are differs. In this vein, the optics provides a more appropriate setting for understanding the character of Hume's experimentalism than the concept of the Principia. As Colin Maclaurin put in his 1748 account of Newton's discoveries, while the Principia inquires into forces acting between bodies and at great distances, the optics explore the hidden parts of nature which are not so easily subjected to analysis because the subtlety and minuteness of the agents. The principles of human nature that Hume endeavors to explore also belong to the hidden parts of nature that can be explored by a method of qualitative analysis and synthesis, similar to the ones advertised in Query 31. Landy in 2017 offers a constant reconstruction of Hume's philosophy of science as aiming at the exploration of hidden processes of the mind. The treatise begins with a setting up of a scheme of fundamental elements for analyzing human phenomenon in terms of ideas and impression. Human analysis begins with a phenomenon from the historical and everyday observation of human behavior, and the analysis proceeds by experiments judiciously collecting and compared in order to arrive at analogies among various instances from the observation of several parallel instances. The products of a comparative analysis so conducted are the principles of various faculties like perception, imagination, reason, whose interaction results in ideas and impressions causing behavior, but their contribution can hardly be measured, and the principles of their interaction can hardly be quantified, not even in principle, so they cannot be mathematized either. Instead, they remain qualitatively different principles of human nature, and the explanation of human phenomenon consists in a description of how these principles, with their distinctive characteristics, figure in producing them. The methodological core thus consists in collecting relevant phenomena, finding analogies between them, and ascribing those analogies to similar causes, thereby reducing a variety of phenomena to regular principles underlying them, while knowing that our knowledge can not transcend what we can infer on an analogical basis from the effects themselves, just as comparing rays of light reveals their determinable properties, which, once determined, can be used in constructing explanations. The comparison of instances of human behavior reveals the principles of human nature with increasing generality and exactness. Salient human phenomena are collected from history and observation, then compared. If analogies or similarities are found, they are ascribed to some principles of human nature that are also compared, grouped, or resolved into more general ones. This process results in determinable properties of human nature, like the faculties of reason, sympathy, moral sense, determining how these properties are actually instantiated in different social, historical, individual circumstances provide the explanatory raw material for singular phenomenon. Thus, we reach the principles of human nature that are the proper aim of inquiry in the science of man. These principles can be used at the stage of synthesis to explain why our impressions and ideas follow one another in the order they do. The outcome of these procedures is the refinement of the theory of human nature. While exploring exceptions and eliminating superfluous conditions, it turns out, for example, that some principles of human nature are universal, some others are particular. Some principles of imagination are then constitutive of human nature, but some others are just contingent on culture or history, or even idiosyncratic and can lead to local superstitions or philosophical chimeras, like presupposing substance as the bearers of properties in scholastic metaphysics. The universal principles provide the fundamental framework of determinable human properties that are actually determined by social and historical circumstances. This explains why certain virtues like courage are evaluated differently in different historical periods, and also why a creature without sympathy, however contingent its degree and direction may be, would count as a monster and not a man. Sympathy is a universal principle of human nature, but the principles and the degree and direction of its sensitivity are determined by the conditions within which it is developed and refined through social interaction. This amounts to saying that Hume's account of human nature has both universalistic and contextualist elements, and this is the outcome of the experimental methodology. It is through a series of successive approximations through a comparative study of changing circumstances that the universal and contingent principles of human nature can be distinguished. Analysis and synthesis, so understood, constitutes the core of the experimental method of reasoning that distinguishes Hume's enterprise from the alternative approach that Newton had termed the hypothetical philosophy. Hume is aware of the distinction and explicitly sides with the experimentalist camp. His methodological pronouncement and commitments situate him in the context of methodological Newtonianism, characteristic to Scottish moral and natural philosophy, who dealt with aspects of philosophy for which Newton had not laid down at the specific postulates upon which future theories were to be built. And finally, analogy. As Hume repeatedly emphasizes, it's important to reveal the ultimate causes of our mental actions, and we have to be content with experience and analogy in explaining any act of the mind by producing other instances which are analogous to it, and other principles which facilitate its operation. Finding analogies between different instances gives one the chance to explain changes and reduce them to more general principles. For human analogical reasoning is the key to most of our everyday and philosophical conclusions in empirical matters. Causal reasoning is partly but crucially founded in our capacity to recognize resemblance among different instances and to extend our inferences based on previous observations to different but unobserved instances. Thus, the recognition of resemblance is at the heart of our reasoning concerning any matter of fact, and the limits of this kind of reasoning are exactly where our capacity to recognize resemblance ends. The proper method of both natural and moral philosophy is to reduce the principles productive of natural phenomenon to a greater simplicity, and to resolve the many particular effects into a few general causes by means of reasoning from analogy, experience, and observation. It is a history, natural and civil as well, that provides the pool of observation from which philosophers, natural and moral ones as well, relying on analogies, can establish explanatory principles. Finding analogies between different instances gives one the chance to explain causes and reduce them to more general principles. In the dialogues, and especially the sections criticizing the design argument, Hume seems to be more critical of analogical reasoning than he is in his other passages of similar methodological relevance. Nevertheless, Philo pronounces analogies and resemblances reliable enough to serve as the sole proofs of the Copernican system. Given that Hume's epistemology, the category of proof, provides the highest level of epistemic certainty available for any piece of empirical knowledge, analytical reasoning is a highly esteemed way of reaching theoretical conclusions in exploring the principles of nature and human nature. Hume's doubts in the dialogues concerning analogical arguments from design primarily do not arise from the weakness of analogical reasoning, but mainly from the uniqueness of the world, which does not provide a sufficient pool of instances among which analogies can be found. Although the cognitive role of analogy is central, it relies on subjective judgment, and so it can have idiosyncratic manifestations. Things are similar in an infinite number of ways, and only some of those similarities can be exploited with the help of cognitive benefit, as anything may resemble any other in an infinite number of ways. Only some resemblance can explain associative relations between ideas. Resemblance of cognitive relevance are therefore not passively detective, but they are actively produced by memory. We remember past instances as resembling. Depending on the resemblances one recognizes among particular instances, one can end up with different and potentially conflicting conclusions concerning the causes of phenomena. Therefore, as Hume puts it, no question philosophies are more difficult than when a number of causes present themselves for the same phenomenon to determine which is the principal and predominant. There seldom is any very precise argument to fix our choice, and men must be contented to be guided by a kind of taste or fancy arising from analogy and a comparison of similar instances. This is one reason why tis not solely in poetry and music we must follow our taste and sentiment, but likewise in philosophy. And while the subjectivity of analogical reasoning is a source of creativity and insight, it also puts the objectivity and certainty of Newton's epistemic ideal beyond reach. Okay, so there you have it, folks. That concludes my deep dive into Isaac Newton. So a lot of information there. Hard to give much insight, and just say that like in the Talmud Hadranalach, we will return to this. Um, yeah, Mr. Boston, appreciate you sticking with this. Hope this is useful to you too in your research. Just kind of like minimally like a book on tape. Um, and just get these words flowing from my mouth to have these ideas in their better form, um, in their best form, in the proper language, and as I said, I'm getting a lot from my research here. It's tough exactly to understand how I'm going to advance or um, what I'm going to do with this. But if anything, just knowledge for the sake of knowledge in its own purpose. So stay tuned for a week in review, and we'll give a greater review. So next time, I will be looking at the French, and we'll look at Descartes and his contemporaries, Mersenne, Gassendi, Arnault, and Bayle. And hopefully after that, I intend to um, do a deep dive on Leibniz, Descartes, and Kant. So a whole bunch of important matters coming up. And so thanks for tuning in, providing feedback. Mr. Boston, you're the only one there with me, so appreciate it. God bless. We'll see you week in review Sunday night. And that's it.